Welcome to the Great Things Summit 2026. I'm Tiffany Nielsen, and I'm excited to kick off a conversation that will set the tone for the entire event today. Because if one thing's clear right now, it's this: sustainability is no longer a future goal, it's an operational priority. Across industries, we're seeing rising energy demand, resource constraints, increasing climate expectations, and growing system complexity. At the same time, we now have powerful tools, AI, IoT, and edge computing, that are giving us entirely new ways to reduce waste, optimize systems, and rethink how we use energy and data. So today's core question is, how do we turn these technologies into real, measurable, sustainable outcomes? I'm joined by three experts, each bringing a unique perspective, starting with Johannes Beekman, who is the CEO and founder of IoT Marketing and TechScope Connect, who are the hosts of today's event. So, Johannes, it's great to have you. Where are you joining from? And can you share a bit about your background?
Thanks for having me, Tiffany. So I'm joining from Austin, Texas, and a little bit about my background. I've been in semiconductors for 25 years, fab startups, process development, then and for the past almost 50 years now, 15 years now, I've been in digital marketing, currently focusing on AI and AI visibility. So it's been a long journey, but glad to be here.
Thanks, Johannes. And next we have Nader Jandagi, and he is the president at UTU Energy Solutions. Nader, welcome. And where are you joining from? And can you tell us about your work across energy and waste systems?
Yes, hi everyone. Hi Tiffany. Thank you so much for having me. I've been fortunate enough for the past 20 years to be involved with the global transition to a low carbon economy. I'm currently just north of Phoenix in Arizona. I've done projects in solar, wind, hydro, natural gas, renewable natural gas, storage, carbon sequestration. I've been fortunate enough to do it not only here in the United States, but also in the Middle East, Europe, and Asia. I've worked with and collaborated with OEM and technology providers, developers, EPCs, IPPs, and financiers. And that's shown me a lot over the past 20 years on where the industry was, where it's going. So very happy to be here today and share some thoughts with everyone.
Thank you so much. And Ration Toolsy, Energy SME from Databricks, is also joining us. Ration, it's great to have you. And can you share a bit about your background and how you're working at the intersection of data and sustainability?
Yes, thank you, Tiffany. Thanks for having me. And great to meet Neda and Johannes. My name is Ration Tulsi. I'm a senior solutions architect at Databricks. I'm also an energy SME. I wear two hats. Most of my career has been at this kind of intersection of data, energy, and technology, and now AI is part of that mix. For most of what I've done is I've worked across the energy spectrum. That's oil and gas companies, renewable energy companies, and the utility space. North America, Europe, Asia, the Middle East. It's been 20 years or so in that space. But recently, in the last maybe 5 or 6 years, I've been focusing on, trying to help operators with like things like dealing optimization to like emissions tracking. And really, where we come into this is like, if you start thinking about a sustainability thread, is sustainability only really works, in my opinion, if it's operational. So if it lives in a PDF that's reported a file once a year, then it doesn't really add much value except in reporting. But if you think about the tech stack that goes with it, if you unify a data sensor, you operationalize the data, you have an emissions data to an open platform, you move from annual reporting to like real-time action. And that's really where we've seen some of our customers move in that direction. And that's where I see the industry being more successful if you start operationalizing that. And that's really things I'd like to work on and help customers achieve.
Thank you so much. Well, welcome to all of you. It's great to have you here as well as everyone watching. So, if you are watching in the audience, please drop us a note. Let us know where you're watching from, as well as any comments or questions that you might have. All right. Well, Johannes, we have been talking about sustainability and technology for years now. What feels fundamentally different in 2026?
We have, Tiffany, and what feels fundamentally different now is that and Rachel already mentioned that sustainability is moving from communications to operations. A few years ago, many organizations still treated this as a parallel initiative, something owned by a sustainability team, a corporate affairs group, or a set of annual reporting PDFs. Now it's showing up in day-to-day decisions about infrastructure, energy use, procurement, logistics, and system design. The other major shift is that the tools are more connected and getting more and more connected. AI, IoT, and edge computing are no longer being discussed and being seen as innovations. They are being used together to improve timing, visibility, and control. And that matters because you're trying to reduce waste and prevent unnecessary energy use or respond to changing conditions in real time. So I also think that the conversation has become more practical. The question is no longer, do we care about sustainability? Most organizations will, of course, say yes. The real question is, can we operationalize it? The companies making progress are the ones tying sustainability to measurable performance, not just intention. And they are embedding it in workflows, incentives, and accountability. And that is what makes 2026 feel more serious, more disciplined, and frankly, more consequential.
And Johannes, what separates organizations seeing real results from those still stuck in pilot mode?
Like I said, of course, you have technology. You need to have the technology under control. But organizations that see real results, it is part of the culture. It has to become part of the culture, not just a KPI chart, unless you roll that KPI chart all the way down. So it has to be part of daily operations.
Thanks, Johannes. And Nader, from an energy perspective, are we finally treating sustainability as infrastructure and not just initiative?
It's funny you asked that question, Tiffany. Over in Europe, it happened a while ago. The shift from just initiatives to being infrastructure in everyday life happened maybe about 20 years ago. Here in the United States, that shift, I would say, happened maybe about 5 to 10 years ago. And prior to then, it was just that, initiatives. It was things like initiatives for the built environment. I'm sure everybody is familiar with LEED, LEED, which kind of provided a holistic way to make the built environment sustainable, right? It had to do with energy management, waste management, demand reduction. That's been around for a while. And then there was folks like, corporates like Walmart and IKEA, where they didn't really know if solar was going to pan out for them or prove it for themselves. But their sustainability initiatives made them do it without really knowing if it was going to prove out. So those first movers really helped the rest of the market prove out that it was actually worth it. And then the real inflection point happened about 5 years ago, 10 years ago, where the investment community and the financiers really truly started to understand this asset class. They started to understand the risks, they started to understand the upsides, and they started not pricing in the risk and really figuring out that the returns were viable and producible. Even to the point where private equity firms, which are typically pretty risk averse, started seeing this asset class as something to invest in and something to put their money in. So ever since that shift happened, which again, I think it really was from the investment community, then you started seeing municipalities and cities put it into the infrastructure code, right? Some places around the US put it in their code that any new single family home has to have a design for solar, for example. The owner doesn't have to do it, but the constructor has to design for it. And also, ever since then, the utilities have really started to realize that distributed solar and resiliency and sustainability is actually good for the grid. It's good for them for their grid to keep it sustainable. So that shift has happened in the US. It is true part of infrastructure now, depending on the state, depending on the locality. But it's really good news. It has happened.
Great. Thank you so much. And Ratian, are we seeing the same shift with data moving from byproduct to strategic asset?
Yeah, I mean, it's byproduct is an interesting word. I would say data used to be considered to be a cost of running operations, a cost of running a business, because you'd have to collect it, store it, and then you would. This isn't the first time we're getting insights from data. We've been getting insights from data for a long time, but now that the scale for getting the volume of data we're collecting increases at an exponential rate, data is no longer this kind of like cost or byproduct. It's now moving into an operational asset itself. And also, if you look at a lot of more organizations, they now think of it more as a commodity for generating revenue itself. So data becomes a stream for creating these value points. You can create insights within your own organization. You can create insights to your customers to make decisions. If you're a utility organization, you want to determine what the cost to serve is. That becomes far more interesting because we want to have a sustainability mindset. We want to reduce the cost in your carbon footprint. At the same time, there is the cost of running operations. If the cost is too high, you will have to drop all the other things to manage that cost. But what if the cost to serve still allowed you to do all three things, which is manage your sustainability carbon footprint, and then also maintain your customer footprint, and you gave a view into your customers so that they can then make decisions as to what products they want to use within the organization. All of that has now become this kind of like data-centric viewpoint, where now we're seeing within our customers that roles have been created where there used to be these data silos or data individuals working in silos somewhere have now been put into the forefront, where you have CDOs or chief data officers now becoming strategic decision makers within an organization versus just being reporting as to how it is. So we are seeing this. It's more than just an asset. It's also a management tool that's been changed. So we are seeing people being empowered to do so, and more importantly, our customers being empowered to do so at the same time.
Thanks. And Johannes, where are AI, IoT, and Edge delivering clear sustainability wins today?
Definitely, we're seeing the clearest wins in environments where timing and context matter. Buildings are a good example. If you can combine sensor data, edge processing, and AI-based optimization, you can reduce unnecessary heating, cooling, lighting, and equipment runtime without waiting for a delayed analysis in the cloud. And that's not theoretical. That's a very practical way to cut waste. Industrial operations are another strong example. When equipment health, energy draw, temperature, vibration, and throughput are monitored in real time, organizations can shift from reactive maintenance to smarter intervention. That reduces downtime, avoids material waste, and often lowers energy demand at the same time. Transportation and fleet operations also stand out. Route optimization, idle time reduction, load balancing, and predictive maintenance can all improve fuel efficiency and reduce emissions. And in agriculture, combining connected devices with edge intelligence can help manage irrigation, fertilizer use, and environmental conditions much more precisely. Where edge computing really matters is in the speed of decision making. If a system has to wait too long, the waste has already happened. The real advantage comes when data is turned into action close to the source, fast enough to change the outcome instead of just document it afterward.
And Johannes, where does edge computing make the biggest impact?
Where you have the biggest delay, where you have the biggest lag, Tiffany. So where when you have to send the data up to the cloud, do your calculation in the cloud, and then send it back, the damage has already happened. So whenever you're in that situation, edge computing will really make a difference.
Thanks, Johannes. And Roshan, how should organizations decide what data actually drives sustainability and what's just noise?
Yeah, I think this is a challenging kind of answer because you have to define what are their sustainability KPIs and what they want to hit, right? If it's reporting across those bands, reporting is fine. Whether it's sustainability within one or two, whether it's within the organization or the vendor organization, and then further out, it really does depend. But I think some organizations in the past, they're getting better at making these decisions. Is they would collect everything and hope that insights will then emerge, and that's a reasonable thing, right? Because you have all these like SaaS applications that can actually collect a lot of data, and you have your internal in systems, but that just increases cost without seeing the value of it. Again, like even though the cost of managing data still is smaller than actually the operations in your organization, there's still a cost to this, right? There's a cost to storage, there's a cost to everything, and I think that the challenge is as long as the data is tied to an action and the action is tied to a KPI that you've defined, I think that is where you start about, and then defining what that is. So there has to be this kind of like connection point of like, if there's an action, what's the action? Tying it. If there's a value, can I track it? And that's where we kind of build infrastructure and data pipelines around it, add governance to that. So that's where I would actually start.
And so, with that, if you had to delete 50% of a company's data, what stays?
Oh, that'd be a little fun. And no, you shouldn't. Okay, so this is a tricky one because the answer is I want to say yes, you should, but actually, it's well, what is important today may not be maybe more important later on, and you don't know that, so you shouldn't delete. So I think all data that is at the physical site, sensory and telemetry emissions, they should all they stay. What data you should remove, and this comes back to my original thing about building these data pipelines and governance is a term that we use a lot, which is called single source of truth. You should aim for a single source of truth rather than redundant copies. So if you have multiple copies of data, I would go for the copies first. Always maintain that original single source of truth because later on, once you start adding information to that or metadata or better insights, you're going to need that original thing to actually go back and see what makes sense. So yes, by all means, all the copies, data's never been used, never been touched. Maybe it is, maybe they are redundant. So define what redundancy is, and then and then look at them. To my point earlier on, I think quality control and quality single source and governance around data beats like size every single time, like beats volumes of data. So yeah, just remove redundancy of data, and that's a good place to start.
So, keeping everything is actually a hidden sustainability cost.
Yes, I would say so, because then what value does it drive? And is there a cost to that? Because you have to manage the system, right? And then if you really want to get deeper and deeper into it, where are you storing them? Is there an energy output for storing it? Are you consuming it? Is there an energy compute cost to actually to actually get the data out? Storing it for just storage purpose has no return, right? So that actually is something to think about. But yes, so keeping everything that has no value is potentially a hidden sustainability cost.
And Johannes, many organizations struggle to show ROI. How should leaders connect sustainability metrics to business outcomes?
Well, the first step is to stop isolating sustainability metrics from the rest of the business. It is part of your business. If a company tracks carbon, energy, water, or waste in one dashboard and cost, uptime, margin, and productivity in another, leadership will struggle to connect the dots. The better approach is to show how sustainability performance affects operating performance. For example, if you reduce energy waste, that's not just an environmental improvement. It can lower operating expense. If predictive maintenance reduces unnecessary equipment failure, that's not just a resilience story, it can improve uptime, labor efficiency, and asset life. If smarter logistics reduce miles traveled, that can affect both emissions and delivery economics. I think leaders should frame sustainability in, let's call it, three business languages: efficiency, resilience, and strategic positioning. Efficiency asks, what are we saving? Resilience asks, what disruptions are we reducing? Strategic positioning asks, how does this strengthen our long-term competitiveness with customers, investors, regulators, or partners? The mistake is treating sustainability as a moral add-on. The stronger position is to show that it is part of how a company operates better. And when the metrics are tied to cost, risk, and performance, our ROI conversation becomes much clearer.
Thanks, Johannes. And back to Ration. If data is an asset, when does it become a liability?
When it's not free, when there's no freedom. Yeah, free is a cost, right? Actually, it has to do with. So I'm a big proponent of open systems, open format, open source, and I think those are winning this fight. I think if data is remained in a silo, or there's a lock to it, or it has a proprietary format, it actually will kill value over time. And there might be good reasons why you would do it. And it could be because it could be a data residency issue. There could be security. There are good reasons to making these decisions. However, if it is kind of like locked away, you don't have access, then the governance of it, the lineage of the data, the quality control and ownership becomes riskier to kind of track and manage over time. And that's when you start keeping multiple copies of it to kind of manage those things, and that adds the additional cost. So again, I think if you want to move away and manage and reduce liability, open formats, open governance is a way to kind of like maintain data as an asset versus a liability.
Thank you. And Nader, let's connect that to energy. So we're moving away from a one way utility controlled grid to a decentralized participatory system. What does it mean for consumers to shift from energy takers to energy makers?
Tiffany, that's a great question. And that shift has been happening for a long time now. It's accelerating. A little bit of history here. So in the US, it was really in the late 1800s that we had our first central power plants, right? And they're already localized in New York, in the Midwest, some in the West. So that all kind of started the centralized power plants back in the 1800s. By the mid 1900s, most of the states in the US had regulated utility commissions. And for the next 50 years after that, everything remained centralized, right? So whether it was a big coal plant, whether a big gas plant, nuclear plant, even solar plants, these were big utility scale power plants, centralized, typically away from where those electrons were being used. Utilities would build those assets, generate those assets, and basically sign up tariffs, right? And we would be takers. We would basically look at a utility, whatever utility is where you live. You would get a certain set of tariffs, whether you're a residential owner or a business owner, and you would sign up for a tariff. That tariff is basically a price and availability, right? So that kind of prolonged on for a really, really long time where we would just be takers. The utility would build these things, would operate these things, basically provide tariffs to us. We would sign up for those tariffs and buy electrons from a generating asset, which would be typically a long way from us geographically. Uh, then what happened in the early 2000s is distributed energy started. And that's mainly with the advent and adoption of solar, right? Because you can put solar anywhere. You see solar on little parking meters. You can put solar on your house. You can put solar on your business. And that really was a fundamental paradigm shift where you, as a homeowner, you, as a business owner, would generate your own electrons, right? That was huge. In effect, you started changing from being a taker of electrons that were made from the utility by being a maker of those electrons, where you would consume those electrons yourself on site at your house, at your business. And going back to the investment and really the financing markets made it very amenable and easy to either own a solar system, lease it, do a power purchase agreement. You still had to interact with the utility, and you still do, in signing up with a tariff. But those tariffs basically now say, oh, okay, now you have solar in your house. You make your own electricity, great. So that fundamental shift of centralized, utility owned to decentralized, residential owned solar, business owned solar, that was a huge time coming. It took a while, but again, a big fundamental paradigm shift in how we see the grid.
And so, Nader, how did DERs and IoT reshape the grid edge? And what risks emerge?
Uh, Great question, great follow on question. So, DER is distributed energy resources, right? So, basically, generally, it's any resource that is connected to the grid and has the ability to either take electrons from the grid or give electrons back to the grid, right? So, we just talked about solar, solar on your house. Battery energy storage, lithium ion batteries. So, like a Powerwall, for example, that can take electricity from the grid, store it, and sometimes even give it back to the grid. Electric vehicles, the advent of vehicle to grid electrons, where you plug in your EV to the grid and maybe you sell electrons to the grid, right? Smart buildings are a big example of a distributed energy resource, where a smart building sometimes takes electricity from the grid, at other times gives electricity back to the grid. So the concept of a behind the meter distributed energy resource, and now in the past 5 years, the advent of a front of the meter standalone storage, which is still distributed within the community, That concept has become very valuable to grid operators and utilities because of the resilience that it provides, right? Imagine in the afternoon where electricity prices are really high and the utility needs electrons from everyone, or maybe a central plant goes down and suddenly the utility says, you know what, great, I've got a solar asset over here, a battery asset over here from these homeowners. I can take those electrons back and use them. And all of that plays into what you've been talking to, which is the IoT. Imagine every single one of these distributed energy assets, whether it's solar, storage, an EV car, a smart building, and really the proliferation into hundreds, thousands, millions of devices that are out there that need to be connected to the grid technically, right? And basically have a system where there's a digital twin of any community, right? Where the SCADA monitoring systems and even control systems operate that. I mean, that is really where distributed energy systems are going. That's the value it provides to the utility and the community. And as with all things, Tiffany, like you said, there are risks. As we connect everything to the grid, as everything is being digitized, and these are valuable resources to the community, security, cybersecurity, right? We then become vulnerable to a bad actor, not only in the past being able to take down a centralized event, but now having the ability to take down multiple distributed energy plants. So, as with any new innovation, DERs bring a lot of positive value. There's risks like security and cybersecurity, but the industry is already starting to address those, and cross fingers will get ahead of the bad actors.
Thank you, Nader. That was a great breakdown. And Johannes, IoT generates massive real time data, but how does that translate into actual production on the ground?
Well, well, Tiffany, IoT has been generated a massive amount of data from the first webinar we talked about IoT. So this has been going on for 7-8 years. What we're realizing now and where we are now with IoT is IoT only creates value if it changes behavior, system settings, or operational or influence operational decisions. Collecting data is not the same as reducing waste. The translation happens when real-time data, real-time signals are connected to actions that are specific, timely, and repeatable. So let's take a building, a factory, or a fleet. If an IoT device tells you a machine is running outside its optimal range, a refrigeration unit is drifting, a truck is idling too long, or a facility is consuming power when occupancy is low, that insight has to trigger something. It might trigger an automatic adjustment, an alert to an operator, a maintenance workflow, or a change in scheduling. That's where the reduction happens. The other point is prioritization. Not every data point deserves equal attention. Organizations need to know which signals are tied to energy demand, material loss, equipment inefficiency, or avoidable emissions. Otherwise, they end up with visibility, but not improvement. So I will put it this way. IoT gives you awareness, but awareness alone is not a goal, it's not enough. The goal is intervention. The organizations getting results are the ones that have built a path from sensing to decision to action to measurable outcome.
Thank you, Johannes. And Rachel, where are companies collecting data and not acting on it?
Yeah. So emissions data is one of the bigger ones. And so what we found is, I think S&P reported that 99% of the Fortune 500 companies are now reporting sustainability metrics, but only, I think, 16% of the world's largest companies are on track to kind of hitting those net zero targets. And there's probably there are good reasons for that. And fundamentally, it's because these net zero targets are not well defined. Different countries different regions have different net zero attainability targets. Some countries or regions just don't have them at all. So, if you're reporting or you exist in these different countries, as most multinationals do, it becomes very difficult to actually achieve those goals when your working country doesn't actually need those targets. And I think the reality is that it's not that they can't act on it. I think the answer is act to do what? What is that action that's needed? is net zero the right answer here? And I think that's something that we are discovering right now, because what we're seeing is that while because we know that they are tracking the emissions data, because we are seeing that the emissions are rising, even though they have these net zero kind of pledges. And that's because the demands from our societies have increased. We want more products, we want more energy, we want more items for our survival and for our growth. So, and then again, at the same time, we have economically developing countries, and they are rising towards post-industrialization right now. So that will also then increase those numbers, and that's happening. You can't tell and you shouldn't, that those countries should not develop themselves and grow. That population wants to, experience a lifestyle that's been experienced by the other half of the world. So we'll see this right now happening. Right. So there are good reasons, and there's some negative reasons as to why it's not happening. But that's it. They are collecting it. It's just acting. I think the answer is to act on what. Reduce sustainability, but maybe that's not something we can do based on demand.
Thank you. All right. And Nader, how realistic is peer-to-peer energy trading, such as solar, EVs, or blockchain?
Tiffany, it's realistic, but there's challenges there. The reason why I say it's realistic is the capabilities and the building blocks are there. And mainly the catalyst for that has been the blockchain, right? The blockchain, which is used for digital currencies and other things, very transparent, very accountable. That blockchain really enables peer-to-peer transactions and really enables smart contracts. So imagine me sitting here in Phoenix, Arizona, having solar on my house, and saying, you know what, I want to monetize that solar. I want to maybe sell it to somebody to meet their sustainability goals. So my ability to find someone, let's say on my street or in my community, or beyond that, in the same city I'm in the state, or even the US, the ability for the blockchain to enable those peer-to-peer contracts. And for me to say, you know what, I'm going to plug my EV into the grid, enable the VTG function, and sign a contract with somebody in Houston to basically buy those electrons that came from my solar system. Those are clean electrons. Strike a price with my peer, strike potentially a time of day where they take those electrons. The building blocks are there, Tiffany, to do that peer-to-peer transaction. The challenges are regulations, both at the federal level and at the state level. The thing about the United States is, as far as it comes to the utility grid, we're not one country. We're 50 different countries, 50 different states. Each state has its own utility commission. And even within each state, there are different utilities. In California, there's 6 investor-owned utilities, 3 big ones, and there's dozens of co-ops. Each and every single one of those utilities has their own regulations that they have to follow. And that is making peer-to-peer challenging from a regulation standpoint. So it's kind of good news and challenges. The capabilities and building blocks are there, but just the regulations and the challenges we just have to overcome.
All right. A follow-up for you here. How do we ensure equitable participation?
I think once you start getting over those challenges, then it's really, the private sector and how they enable hardware solutions. And I'll give an example. The other day I was walking down the street and I saw a bunch of kids on electric scooters, right? For example, making those electric scooters very affordable, especially for disadvantaged communities. Imagine a kid going on that electric scooter, going back home, going in and doing their homework, and then plugging that electric scooter back into the grid, and through the use of smart contracts, selling their electrons to somebody else and basically making their lunch money, right? So that's a great example of, in essence, this peer-to-peer that we talked about, really enabling disadvantaged communities and equitability between peers, right? And I look forward to that. I think the private sector, once some of the challenges have overcome, are going to give more solutions to the market and anyone, including kids, ways to monetize the grid.
And Nader, how do you see the roles of fossil fuels and renewables evolving over the next decade?
Fossil fuels and renewables in the past has been kind of a very confrontational outlook. And honestly, it's very complementary, especially these days. As the grid expands, as the demands on the grid grow more and more, I think everybody realizes that it's an all of the above solution. I think, unfortunately, politically, there's different camps that say, hey, fossil is the best way to go. And hey, me being in the renewable energy sector, I know people in the renewable energy sector that says, you know what, forget about fossil. Everything we need to do needs to be renewable and sustainable. I think the reality of things, especially given the growth in AI and AI consumption and data center, is we need all of it. And projects these days really realize in a pragmatic way, and investors realize in a pragmatic way, that, you know what, it's fossil, it's renewables, they have to work together and play off of one another to really provide the reliability that the industry needs and the pricing that the industry needs.
Thank you. And Ratian, despite rapid investment in renewables, global demand for oil and gas remains strong. So, are we underestimating how long hydrocarbons will stay central to energy systems?
Yeah, I think it's a valid question. It's actually a great question, good follow up. And actually, I want to kind of follow up what Nader was actually saying, because I used to have a house and it had solar in it, and I was doing exactly what he was saying, where you could sell back into the grid, you can then offset on days you want there, and you could actually almost reduce your entire cost of investment of energy, and then at the same time, actually fundamentally providing a lower cost of energy for another consumer down the stream. So your home became its own kind of like turbine. But that in itself is not a scalable solution, because it fundamentally needs a roof and a home that do it. It does need a financial investment, which is sometimes out of the reach of most people. It's also not equitable in the sense that while we do say there's rapid investment, it really doesn't help people who live in apartments or have like low income homes, so that they can't benefit from this. So then it does create two different classes of people: people that will have good access to energy, and those don't. But at the same time, traditional hydrocarbons does provide that at a very low cost, and it's designed towards traditional hydrocarbons, and it's going to be there for a long time. I think the International Energy Agency says oil demand is going to reach, I think, 102 million barrels by 2030 per day. That's it's going to plateau, and we see the demand rising because hydrocarbons is easier to get access to. It's a lot of energy in a small amount of volume per capita to go out there. But the answer is, and again to Dana's point, it really used to be confrontational, but it's completely complementary. Because if you head out to West Texas, you will see like these artificial lift, which are these nodding donkeys we see often. The traditional view of the of like West Texas or anywhere. And next to it is actually a little mini wind farm with solar panels actually powering that, because it's an isolated energy system out there. Why pay for a massive grid when you can actually keep this going, right? And vice versa. So I think the smart play is addition, complementary, not replacement, right? And this kind of mix of this hydrocarbons operations become cleaner rather than scaling it down is where we'll see most of things going is actually getting towards.
And to further expand on that, Ratian, how's oil and gas evolving, both operationally and philosophically?
Yeah, it's going through its phase, and I think they're moving beyond just this. I think they've tried different things, right? I think there are some large national, international multinationals who have tried big things and they've been unsuccessful, and some has been an economic decision where like they've tried, it's not been successful. Some of it has been political. We can't ignore that factor because politics changes how we invest, how we buy, and how we move. That has impacted kind of like refocus on traditional hydrocarbons versus on the renewable side. And that has happened. And that might change in the future, and that will change depending on how things go into it. But if you look at the industry itself, it's not buying any new large assets. It's fundamentally managing its existing portfolio of existing technology out there. And they're using technology to kind of like build things like digital twinning, agentic systems. They want to operationalize it. They want to make the operations cleaner is one way of saying it, but actually more efficient, reducing its cost of energy to run these systems. That's, I believe, is where they're actually looking into it. They also are looking into other alternate energies as part of its mix, bringing in hydrogen. Like you'll see, Oklahoma is fundamentally, it's a natural gas pipeline system. They have this infrastructure in place. They'll be looking at like, how do I move and migrate towards hydrogen as another system of energy? And because they already like built for this, so they'll look at that. Data and AI becomes this accelerant for this to like make these decisions to reduce the cost of it and also manage the existing infrastructure. So they are moving. Philosophically, they've taken it, and I've seen the most conservative companies that I was surprised with, and in a good way, make those decisions for not just survival, because they want to have growth, want to exist in the future. They still want to have their brands out there, and they're making the right decisions, I think, right now, versus just this like gigantic philosophical swing, either way, left or right.
Thank you for that. And Johannes, later today, we have a great session on RNG, where Maureen Kinua will discuss renewable natural gas as sovereign energy. So, how should governments rethink energy independence when waste becomes fuel?
I think, Tiffany, that this requires a broader definition of energy independence. So traditionally, governments have thought about independence in terms of imported fuel, centralized generation, and large-scale supply security. But when waste streams can become usable energy, the conversation becomes more local, more circular, and in some cases, more resilient. So renewable natural gas is interesting because it reframes waste as a resource. Instead of seeing agricultural waste, landfill gas, wastewater byproducts, or organics as disposal problems, governments can begin to view them as part of an energy strategy. That does not mean RNG replaces every other energy source, but it can strengthen regional energy diversity and reduce dependence on purely linear supply models. It also changes the policy question. Governments need to think not just about generation, but about collection systems, infrastructure, incentives, permitting, and measurement. If waste is going to become fuel, the physical and regulatory systems around that conversion matter most. So, more broadly, sovereign energy in this context means building more capacity from within the realities of your own region. That can make the system more adaptable. And in a period of supply shocks, infrastructure pressure, and climate stress, adaptability is becoming a very important part of energy independence.
Thanks, Johannes. And later today, we have another great session on carbon capture. But Nader, where does carbon capture have the most potential?
Oh boy, carbon capture is a big one these days, Tiffany. Thank you for asking that. I would maybe segment carbon capture into three main areas. Direct air capture, right? Once it gets into the atmosphere. And then before it gets into the atmosphere, pre-combustion capture and post-combustion capture. The challenging part about direct air capture once it's in the atmosphere is it becomes diffuse, right? So collecting that carbon out of the atmosphere can be quite costly. So I think the most potential in the short term is really the other two, pre-combustion capture and post-combustion capture, before it gets into the atmosphere. Pre-combustion is typically when you separate out the hydrogen and the CO2 before you combust it, and then do something with the CO2 at that point. Post-combustion is basically, on-site at whatever generating plant, fossil plant. And typically these days, it's really an afterthought. It's a bolt-on, right? Hey, let's do carbon capture at this coal plant or at this gas plant. So I think the most innovative potential short-term for investors is these quote-unquote bolt-on solutions for post-combustion. And I've seen some pretty innovative pre-combustion solutions come as well, and I hope investors get on top of those as well.
Thanks, Nader. And circular tech and e-waste, just something that's dear to my heart. So I should probably have more of an emphasis in this conversation, but we're trying to cover a lot of ground. So, Johannes, what innovations are reducing emissions, waste, and inefficiencies?
The most useful digital innovations, Tiffany, are not always the flashiest ones. In many cases, the biggest gains come from better visibility, better timing, and better coordination. Digital twins are one example, and it was mentioned earlier. When organizations can model facilities, processes, or infrastructure in a way that reflects real operating conditions, they can identify inefficiencies before they become expensive or wasteful in the physical world. Another important area is predictive analytics tied to maintenance and asset performance. If you can anticipate failure, drift, or abnormal energy use, you can act earlier and avoid both waste and disruption. Smart building controls are also making a real difference, especially when HVAC, lighting, occupancy, and environmental systems are managed as an integrated whole instead of separate layers. And I would also include supply chain visibility tools. Companies often underestimate how much waste comes from poor coordination, overproduction, unnecessary transportation, excess inventory, and lack of traceability. Digital systems that improve planning and transparency can reduce those hidden inefficiencies. And then there's automation at the edge. When systems can respond locally and quickly, they can prevent loss in the moment. And that's often more valuable than analyzing the problem later. So the digital innovation that matter most are the ones that move organizations from delayed awareness to operational precision.
Thanks, Johannes. And Roshan, there's a lot of hype around AI. But how do you differentiate between basic chatbot applications and truly agentic AI systems that can take action in energy operations?
Oh, yeah. The chatbot is a pager, and an agentic AI is your iPhone. If you think of it like from that. Yeah. And to all the kids out there, pages is something everyone used a long time ago. That was it. So a chatbot will answer questions, an agent will take action. And that's really the difference is the autonomy. A chatbot would tell you a pump might fail, what an agentic system will actually do in a risk evaluation. It would check different systems. It'll look for inventory. It can schedule maintenance. It can actually update a work order. It can do multiple things without a human in the loop or with you in the loop, depending on the level of access. And I think this is where the systems are moving away. So a chatbot could be an advisor, while an agent could be an operator. So AI advisor to AI operator. That's really where we're seeing that's the fundamental difference in that. And what that requires is fundamentally trust in the data, clear guardrails, governance around it, and full a full audit trail to actually track what it is. Those are really the main two differences between the two. It's think of it this way: chatbot's basic uses and an agentic AI system could be an agentic employee in your organization, depending on the roles of access to do so. And there's a whole bunch of follow-up you can have on that as well.
Well, that's great because I do have some follow-ups for you. Should there be limits on what decisions agentic systems are allowed to make in energy systems?
It depends on how you define it. So the answer is yes, there should be limits, the same limits as you would apply to an employee in your organization. And because just because there's humans in the loop doesn't mean every human should have access to critical systems or decisions in the system. It depends on you. So it has to do trust and governance and the right access to it. So the same with the agentic system, because they'll have command and control access, even viewing data. You have to have guardrails in place for that governance layer, and then autonomy built in to make decisions, but also safety features in place that they kind of go right. The same as a human employee. Think of an agentic employee the same way, right? What access they get access to, depending on their skill level, and how do you trust them, and should they be the right entity that's looking at and making decisions on that place? So, be exactly the same way. You should restrict information to the wrong people. Same with agentic users.
And so, Roshan, what's the biggest risk of letting AI agents act on incomplete or low quality data?
Yeah, it's that's exactly right. It's low quality data or incomplete data, and that's what your agencies work at. Even the best agent that's built on the best model that's super smart, has like a physics based system behind it that's smarter than all of us put together. It can make confidently wrong answers. And I think I'll talk about this later as well, right? So I think what we found is that I think Gartner said that 30% of AI projects get abandoned as proof of concept because the data quality is actually the issue, right? So I think it's fundamentally has to do with like AI will not hesitate to make a decision when the data is bad. I think it's getting better and better. And the hallucination part is kind of we're dealing with that right now. It's we're eliminating that. but it will, if you ask it a question, it will answer it faster. And then how do you trust that answer? And that's fundamentally the data and training about. So I think that's something you have to be careful about is confidently wrong answers. If you trust that, and if you go completely on that, then you could put yourself at risk.
And so, if we move towards agentic AI managing critical infrastructure, what are the biggest risks, technical, ethical, and operational, that keep you up at night?
Yeah, it follows exactly that point. Is this confidently wrong answers? Is that if AI is making a bad decision in a black box, it's like compounding these errors upon itself in a black box. If you don't have access to that, you can't audit that. You won't know where it's kind of making that decision. And because it can calculate and it can consume so much information and data and make this analytic analysis in microseconds, you may not, and it takes an action based on that. It may be too late to actually rectify that. Again, to my point way earlier, is open systems that are auditable, open data formats. You can actually go back and look at it. It has to be auditable. There has to be governance around, and there has to be some observability. It is true that we don't need to have a human in the loop for every single interaction, because that's just not how it's going to scale. But I think that there should be some auditability action on that to make sure that it actually is performing. Do a like quarterly review or something, depending on, like, is it functioning, is it costing, is it making sense? So these are things that these are things that worry me a little bit about. Like, if you have an AI in a black box that's making these bad decisions, how do you know it's bad until it's too late? And then, how do you see it? Right. So these black box systems are where we'll fail.
Thanks, Rashid. And next, let's talk about AI, data, and the energy collision that's happening. And so AI is driving efficiency, but it's also increasing energy demand. So how do we balance this? I'm going to bounce this back to you, Rashid. How should the industry balance AI benefits with its energy footprint?
Yeah, I think there's a little bit of a trade-off, right? And we're seeing this now because this is something we should talk about, is this demand for energy, and that AI data centers. There's clearly a demand increase in AI, right? Because we're seeing AI companies lead the S&P. We're seeing its use in a positive way. So we are seeing that AI is a decision maker, and companies that have AI are more successful than those that don't. So there's a demand for it. But those data centers are getting increasing more. There is going to be a demand on the grid, and so does a utility company. Where does it provide energy to? The AI company or the consumer downstream, and there's a balance into that, right? So who can pay that bill, and how do you balance it out? And that's something to think about, right? And I think Satya Nadella said that, and I think he said it well. It's like, if you lose social permission to use the scarce energy for AI, then it doesn't really matter what AI tokens are actually generating, like improving output, right? So, like, we need to find this balance of positive use of AI and kind of work it out, right? But also, then I think it comes back to, how do we reduce this footprint? Is not every problem needs to be solved by AI. It can, not every problem should. Not every problem needs a large language model being processed for it. We survived as good as a societies until now. We don't really need. Not every problem needs it, but there are some problems that do, and they benefit from it. Really complex ones do. I think it comes back to, like, my job, like building efficient architecture, right sizing models, open source technology. I think those will help understand our footprint and its value that AI brings. And the goal should be this, like, intelligence per wattage, not just raw intelligence, right? So, like, the cost of intelligence and its wattage. I think we'll figure this out as both these things, the demand for energy grows and the value of it grows, right? Because this is all new to most of us right now, right? This increasing use of AI, all of this is new, and we're figuring stuff out. And I don't mean that like in a nonchalant way. I think this is new and exciting, scary at the same time, and we'll have to come. There'll be a collective, like, sigh at some point as to where we're going with this thing.
Thank you. And so, Johannes, how large is AI's energy footprint, and what resources does it require? Can you tell us more about that?
Well, it's clear that AI has a large energy footprint, and you're talking about megawatts per data center. And the way to make it clear how big the impact is, every time we build one of those big data centers, you see that power generation, either nuclear or whatever, is part of the calculation. So um, when we build a data center, we need to immediately add power. Then the second thing is, if you don't have a local power supply, power source next to your plant, now you're talking about you need to draw it from the grid. So the grid needs to be expanded. So it has it's megawatts, tremendous amount, but it has a large impact because which goes beyond electricity of just the model training and inference. You're talking about large-scale data center capacity being built here in the US in every state. You're talking about constant power availability. You're talking about, of course, cooling, significant water use in some facilities, advanced semiconductors, network infrastructure, and then, of course, you have major construction and land resources as new capacity is built out. So this is not just software. This is physical infrastructure that is being built out to support the structure. The scale, of course, it varies by the workload, but the workload is just rising. It's going through the roof. But the point that I'm trying to make is clear. AI places real pressure on the current power systems, cooling systems, supply chains, and data center infrastructure. But we wouldn't be talking about AI if it didn't at the same time have large benefits that we all use on a daily basis.
Thanks, Johannes. And AI isn't alone. Crypto also consumes massive energy. So, Nader, what's often overlooked?
Yeah, the theme of the day, of course, as Rishon and Johan said, is AI. Everybody is kind of deer in the headlights on the power consumption needs of those solutions and the hockey stick curve of how much they're going to grow. But yeah, let's not forget about digital currency, right? That's been around for a while. I think currently, if you look it up, the estimates are to mine a Bitcoin these days is around 500,000 kilowatt hours. It's half a gigawatt hour. It's not trivial, right? And as Bitcoins become fewer and fewer, they will get more and more costly and more difficult to mine. And Bitcoin is just one of them. And that's just the mining of them. The transaction costs of people, exchanging coins, monetizing them, trading them, that's going to come into effect as well. Recently, with the administration basically putting forward the Genius Act, really is making it more accessible for people to interact with digital currencies. So I think, let's not forget about digital currency. Eventually, a Bitcoin transaction or a conglomeration of these coin transactions is going to be as much power as a small country consumes, right? So we can't forget about that. The other thing I don't want us to forget about also is the metaverse, right? Famously, a few years ago, Google named its parent company Meta and invested billions of dollars into the metaverse. And I think a couple of weeks ago, they announced they were shuttering that business, right? Because they're putting all of their investment into AI. But I would say don't count the metaverse out. I think that's going to come back at some point. And at that some point, that's going to burn up a heck of a lot of cycles of power consumption as well.
I think you're absolutely right. And so is quantum and robotics. I'm not sure how much robotics will play into it, but I think crypto and AI is definitely where the attention is right now. Mm-hmm. But Nader, are co-located microgrids becoming standard for data centers?
Tiffany, I think that's the writing on the wall, both practically and politically. I don't know if everybody saw a couple of weeks ago, all the heads of the data center companies were invited to the White House. I think there's a lot of anxiety in all communities that electricity prices are going up, specifically because there's such a need and such a demand from AI in those hyperscaler locations. And everybody's starting to figure out that, yes, that power generation needs to be co-located where the draw is at the hyperscaler locations. So now the discussion is, okay, who are the stakeholders we need to bring together to make that happen? It's the landowners, it's the utilities, it's the utility regulators, it's developers, financiers, IPPs, and it's everybody coming together and figuring out, okay, is this 500 megawatt, 1 gigawatt co-located power plant? What is it? How does it work? Is part of it behind the meter? Is some of it front of the meter where those electrons go to the utility and then go to the hyperscaler? Is it a microgrid? We've never seen microgrids at this scale. But this is really the challenge, to put generation where the hyperscalers are. Now, the exciting thing about that, coming from a solar background, is we are now seeing solar power plants being sited in states where we would never be doing solar before, right? Solar markets used to be California, Texas, Northeast. Now these hyperscalers and co-locating power are like in Wisconsin, Indiana, Iowa, and we're putting solar plants there. So that's kind of exciting. But at the end of the day, yeah, I think the writing is on the wall, both politically and practically, that these power generation units need to be co-located where the hyperscalers are.
Thank you, Peter. And Ratian, what role could SMRs play in powering next-gen compute?
Yeah, that's important because it goes back to the mix. So SMRs are these like small modular reactors, little nuclear. Well, I mean, not nuclear, but to power these hyperscalers, to power AI, and also then like we aren't just building energy for hyperscalers alone. We're building energy for our growing societies and communities as it grows, and the demands of our lives grow. We're going to need different energy sources to do so. And I think this is where these SMRs can actually commit. I mean, they're relatively stable. There's a carbon-free baseload power. It's smaller. We are seeing Google now, I think, targeting over 500 megawatts of SMR power data centers by 2030. And we'll see the other hyperscale probably scaling in a similar way. The US is projecting over 6 gigawatts, I think, by 2035. The SMRs are supposed to actually then help offset. And yeah, I mean, the economics are there. The cost of managing is there. I think SMRs will be an important part of this energy mix conversation as we go into it.
I'm glad you brought up energy mix. Nader, what does the optimal energy mix look like for a 1 gigawatt data center?
Yeah.
Oh boy, yeah, kind of going back to what I was talking about. How do you provide 1 gigawatts worth of power for a hyperscaler location? And again, I'll say it's a mix of all of the above. I think everybody realizes pragmatically in the short term, the majority of that 1 gigawatt or however it needs to be is going to be natural gas, right? And especially in the past decade of the US with fracking initiatives, we have natural gas available. That's going to be the backbone and the baseload provider for these hyperscaler locations. But then the consumers of this electricity, whether it's Amazon Web Services or Google or Oracle, thankfully, all of them have very robust sustainability goals where they're mandating, in effect, that, listen, out of that 1 gigawatt, wherever in the US it needs to be, 20 to 30% of it has to come from renewable sources. So it's dragging along solar, it's dragging along battery energy storage to be co-located with the natural gas production, right? Which is great. So definitely natural gas is going to be the big one. Renewable energy is in the mix, 20 to 30% from what I've seen these days, depending on the locality. Going back to what Ratian was saying, everybody's looking at nuclear in whatever way, shape, or form, SMRs. Everybody's concerned that nuclear just has too much of a long lead time. But I think last week I saw an announcement that TerraPower, which is, I think, a Bill Gates investor company, was able to secure the first nuclear permit from the federal government in 8 years. That's a big deal. And they put in for that permit, I think, only 2 years ago. So I think everybody's looking at nuclear SMRs. For the foreseeable future, in the short term, I think it's just natural gas, solar, renewables. And then let's not forget about that natural gas, which is giving off all that carbon and going back to carbon capture. Uh, Everybody is mandating that carbon that is being generated by the majority fossil is somehow captured and either sequestered or used to make a product. Right? There's great companies out there. There's a company out there that makes concrete out of the carbon. So not only co-locating everything of the energy mix, but grabbing that carbon and doing something with it.
I think that's a very important piece of the conversation there. And Nader, I have another question for you. So, why do corporations, especially data centers, pursue sustainability? Is it economics, regulation, or reputation?
That's changed over the years. And the Europeans have been far ahead than the US. The Europeans have kind of mandated, and a lot of the executives are directly compensated, money wise, bonus wise, for meeting sustainability goals. Here in the US, over the past 20 years or so, the majority one reason has always been savings, money, right? Especially for behind the meter solar projects, for example. Is putting solar on my facility and consuming those electrons myself, does that save me electricity? Is there savings there? That's been really the main driving force for doing that. Over the past 5 years, companies have kind of pivoted because they now know with this new generation coming up that reputation is a big deal for them, especially for these data center companies that sometimes get a knock of, oh my God, we're using so much power and it's dirty. Employee attraction, employee retention, right? The new generation who's going into the workforce actually cares that a company has sustainability goals, right? Even if those sustainability goals are at the same price or maybe make the company spend a little bit more money, it's valuable to them because they attract the talent, especially in the technology sector. Also, I've seen from the investor side, especially with the advent of the impact investor, more and more investors are investing their monies in companies that have sustainability goals, right? So it's kind of shifted from, hey, I want to save money to I want to attract investors and employees. And looking towards the future, it's really hedging against regulations too, right? We all know about the Clean Power Plan that one of the previous administrations had put forward. That went away. But I think most corporates and hyperscalers know that the tide changes and it turns. And the next administration might bring back some form of the Clean Power Plan, and they want to get ahead of those regulations.
Thank you, Nader. And Rayson, what's one overhyped narrative and one underestimated one?
I think the overhyped narrative, if you're thinking about things like AI, is AI can solve. Let's say AI can solve sustainability. AI alone can solve sustainability. That's an overhyped one, right? And it's fundamentally is because it can't. AI is not a solution maker. It's an accelerant to it. Right? You still have to take action. So without the data sources, the platform, the governance, AI will just make bad decisions. That's that. So it's part of the solution, not just the solution itself. Right? So I think that could be it. Underestimated would be, again, going back to this thing is how do you operationalize some of these decisions and the technology? It is really open source, open system, and open formats. Those three things. Those things actually help enable and scale and help de-risk a lot of issues that we are seeing right now around it. I think people underestimate that, and I think the data speaks for itself, and growth and access to better decisions comes with openness.
Thank you. And Johannes, kind of looking at putting this into action, how should leaders better connect sustainability metrics to business outcomes?
Well, first of all, leaders should stop treating sustainability metrics as a separate scorecard and tie them directly to core business measures such as cost, uptime, risk, efficiency, and asset life. If energy use drops, show the operating savings. If waste is reduced, show the margin or process improvement. If better monitoring prevents downtime, connect that to resilience and productivity. The key is to frame sustainability not as a side initiative, but as part of how the business performs.
Thank you, Johannes. And Nader, how can the industry stay resilient amid policy uncertainty?
Wow, that's a great question because we're really getting the yo-yo with policy here in the US over the past 10 years and even 20 years. Um, I think one of the benefits of the way our government is structured here in the US, as compared to Europe, for example, is again, the US isn't necessarily one policy country. We're 50 different states. And every state has its own initiatives, right? As an example, I'll give is years ago when the US exited the Paris Climate Agreement, literally the next week after that, 10 states, California and 9 others, basically said, you know what? We're still going to adhere to the Paris Climate Agreement. And those 10 states made up a third of US GDP. That's a big deal. So I think that definitely plays to our favor with these big policy yo-yos is the states and localities step up to the plate and basically in the mandatory markets put in policies in place in the compliance markets. But then also in the voluntary markets, corporations and corporates step up to the plate and give certainty to the market that, even though policy is going one way or another at the federal level, on the ground, it still goes. And those companies that can weather the storm and think long term as far as investing in the right technologies and the right solutions, they'll do very well.
Thank you, Nader. All right, we're going to enter the rapid fire portion of this session, and I'm going to do a quick round with short answers. So anyone can jump in to answer these.
Okay.
So the first one is, I don't have buzzers, but you guys can just jump in. What defines organizations that win in sustainability in 2026? What defines organizations that win in sustainability in 2026?
Oh,
Well,
I'll take
also mentioned. Take it. Okay,
Go ahead. Go ahead. You take it. Go.
Well, the organizations that wins are the ones that build sustainability into how they operate, into the daily operation. It's not just about how you present yourselves. You need to connect everybody from leadership all the way down to operation, IT, finance, and facilities, instead of leaving the work to one team. Those are the winners.
Nader, did you have something to add?
I think companies that are pragmatic are going to win, right? Companies that say, I'm only going to do solar and that's it, they're not going to win. Whereas developers and investors that are pragmatic and say, you know what, I'm going to do some gas and solar along with it and drag it along, those are the companies that are going to win.
What about you, Rayson? What do you think?
No, I agree with with both of them. Actually, Johannes, I had exactly the same answer, right? So the thing is, no more reporting. Take actions on the decisions you have. You already have all the data you need. You don't need any more. You can actually start making decisions straight away that impact your operations. And I think those companies will actually succeed in sustainability. And then to Nader's point, just don't be myopic about, and don't be a purist. If you want to solve big problems, you're going to have to think about where are these problems and how do I work together.
I would say companies that are agile, if they're able to move around things as need be because things.
Please change.
All right, next question. What is the bigger gap, technology or execution?
Execution. The technology is there, right? So right now, I think if you think about it this way, so the data says that data center investments will surpass oil and gas spending. So $580 billion versus $450 billion. Money and technology is here. The question is, how do you align them and execute on them so you can actually solve the energy and data challenge? It's just execution. That's what's missing.
All right.
I'd agree. It's execution. Even though some of the technologies are pretty immature, I think there's a whole new generation of investors that are willing to invest in those technologies, and it's just about execution.
Johannes, any comment?
I would just add to that the technology is there. Meaning you can pick and choose whatever technology you need, come up with your own solution. But it needs to be executed and executed well.
All right. And the next rapid fire question. What constraint will define the next decade? Energy, data, or something else? Oh, we're out of water. We're out of power. No, just kidding.
Um, I'll take a stab at that. I think a big constraint has nothing to do with the energy or data. It has to do with the very polarized politics that we have and the echo chambers, right? Somebody watches the news and they get a snippet about something. In reality, sustainability is bipartisan. It really is. When you really talk to people and you have a nuanced discussion with them, everybody kind of agrees that, you know what, it kind of is the way to go. But then when you have these echo chambers and all these influencers looking to make money and they say something that wants to grab attention, that kind of distracts from the narrative and the discussion.
All right, I have another rapid fire question for you. Does more data lead to better outcomes or more complexity?
Better outcomes. We can manage the complexity.
Anyone else?
If you get out of analysis paralysis, yes.
Yep.
Because more data, some people have the tendency to just kind of stare at it for a long time and not do anything. And the biggest risk is not doing anything.
More data with the correct analysis will give you the better outcome.
All right, and last question in our Q&A here. What does a truly intelligent, sustainable enterprise look like in 2026?
Well,
Keeping in mind that Facebook is actually considered net zero, but it has Moltbook, and that is racking up a huge amount of energy. And it's just agents on there. It's not even serving people, it's serving other agents. And they're still net zero. I just don't know. But what is it?
and that's my point earlier about like how do you define net zero? Maybe that's an ill-conceived kind of like concept to have. You can offset that any way you want to, and then it has almost no meaning. If you really want to be truly sustainable, like what are you trying to achieve with that? And I think a truly intelligent company that's well, I'll rephrase that answer. For your answer, I believe it's a company that's being completely transparent and that the data and the intelligence around it and the insights they're actually sharing is auditable and traceable. I think like companies are there right now; they can do all this stuff, but I think if that is auditable, traceable, and transparent, whatever the answers may be, I think those companies that will be more successful, and then that's what we can achieve in 2026.
Yeah, and those same companies who can really look themselves in the mirror and realize that, you know what I've been doing in the past may have been a little bit of greenwashing, and come to the realization with the help of their employees and stakeholders that I really need to actually do the right thing and not greenwash. And I think that's happening, honestly, here in the US.
Johannes, anything to add?
Yeah, greenwashing, but also coordination and making sure that whatever you're working on, incentives are used to use resources more intelligently.
Perfect. Well, thank you so much. And if there's one theme from today, it's definitely this. The sustainability is no longer a separate initiative. It's embedded into how systems are designed, decisions are made, and organizations operate. And the real shift is this: it's not just about better technology, it's about using it with intention, alignment, and control. So, thank you so much to all of our panelists and to all of you who are joining us. We have an incredible lineup ahead. So, stay with us. If you happen to be watching on one of our streams, you can still register to attend all of the sessions, and you can do so at iotmktg.com or techscopeconnect.com. Thank you so much.
Thank you. Thank you, Tiffany.
Hello and welcome, and thank you for having me here at the Green Think Summit. Today's presentation will be about the AI Energy Challenge and why the power observability actually matter for sustainable cloud computing. So before I start, let me introduce myself. I am Zohar Bilal. I'm currently about to finish my PhD, so I'm still PhD candidate at ATS Montreal, Canada, and I'm focusing mainly on sustainable cloud computing and energy-aware serverless frameworks. And I'm mostly also focused on how to apply AIs and ML in order to optimize the performance and reduce the energy the energy and environmental footprint for cloud native system. And during my academic journey, I also enjoy long internship with Ericsson, and I'm also a champion member in the Green Software Foundation. So I think about today's presentation, I think the energy consumption right now does not need any motivation anymore, because the impact of a global warming is not actually a research question anymore. We can see it and feel it in front of our eyes every day. And while there is some groups that are working hard in order to save our planet and ensuring or introducing more sustainable solutions, there is others they are trying to speed up this destruction process. And here I'm referring to the giant of AIs. For example, OpenAI just recently announced that they will they need to secure 250 gigawatts for their data centers, and this is just in the next 10 years. And this amount of energy consumed by its data center is actually the amount of energy that can be consumed by a nation like India. OpenAI is not the only one. For example, Amazon, they also announced they will build their 2.2 gigawatt data center. It was also in India, and this data center even is small, but it's consuming the half of the entire city. Again, the list going on. For example, also OpenAI in another data center, they announced that the power they need is actually for their data centers is actually the power of New York and San Diego combined. So imagine how much power we need in order to power these AIs for the next wave of AI-based workload. But when we are speaking about the energy efficiency, or we want trying to make any sustainable effort, for example, energy optimization, evaluation and benchmarking, and also taking some actions and control, the heart of all of this is the power monitoring, because we cannot actually optimize or taking action for something that we cannot see or measure. And why the power monitoring actually is very complex in a containerized environment, or specifically in the cloud native environment, which is the backbone of all our services, because the cloud environment stacks or the infrastructure is very complex. For example, at the hardware layer, we have different hardware vendors and each vendor have its unique way to modelize the power and unique way to consume the power. And on the top of that, we have some virtualization layers, and then we should not forget that we need some orchestrators for our pod and containers. And then we have our application in a form of microservices or containerized pod or like this. The idea here for having all this abstraction layer is to add more flexibility. And yes, indeed, it added more flexibility. But at the same time, it's making the power optimization or monitoring is very complex, because actually we can measure the power only at the hardware level. And this gives us the question, because we don't need the power by the compute node, but actually we need it by a container level. And this what led me to asking the question, okay, so what we actually need to enable the full power observability in cloud native environment. And in order to do that, I did define 9 requirements or 9 challenge in order to fully enable the power observability for these environments. So first of all, the first challenge or the first requirement that we need is that this tool should monitor the power at the container level, regardless of the underlying infrastructure. For example, whatever this container is running on the top of VM or in bare metal, whatever the hardware is. So we should be capable to monitor the power at the container level. And second, since the power is not single value, because it is not like CPU usage, because the power we should, because for example, taking a container, it will consume, for example, CPU, memory, storage, IO, and GPU. So we have to track the power of this container at each hardware component, how much it consumes, and we aggregate it. So this is what I mean by support multi-domain power. So we should have the capacity to track the power consumption by container in each hardware component. And the third, I think, is also very important, which is the accuracy of the tools. Because if the reporting tools give us just a random or worthless data, these data cannot help us to making any decision or creating any optimization systems. So we need to deliver trustworthy and reliable data. The fourth requirement that I see very important is the low overhead power monitoring, because in order to deliver power monitoring tools, because power monitoring tools is always rely on like machine learning models in order, because we need to collect performance metrics, and using machine learning models, we can derive or estimate the power consumption. But if the entire process actually like is very heavy or consuming a lot of resource, the cloud provider will never accepting that. Imagine that, for example, you have tools, it will consume like, for example, 10% of the total CPU. So it will be heavy for operator to allocate this amount of resources only for monitoring power. So we need very lightweight power monitoring tools. And also, since we are in a cloud-native environment, so the tool should follow the best practice of the cloud-native environment. For example, it should not be very complex in the way how to install, maintain, update. So it should follow the regular practice that we already use. For example, using Helm chart, operator in order to easy installations, easy reconfiguration, or updating and maintenance. And in the same path, the tools should also support the different orchestrators that we already have them at the cloud native stacks. For example, Kubernetes, OpenShift, and so on. Number 7, also, it's actually the seamless integration with the telemetry stack or the observability stack we already have. Because in the cloud native or systems, we already build a very mature monitoring stack. That's, for example, Prometheus, Grafana, InfluxDB, OpenTelemetry. So all these tools should be reusable in the power monitoring. For example, the power monitoring tools should not have a very customized way to report these power value. It should be integrated with what we have actually as a monitoring stacks in order to be easily integrated. And number 8, which I call it the transparent power aggregation, because when we deploy an application in the cloud native system, so the application will be a set of microservices that can be deployed on different nodes on the cluster. So in order to get the power by the entire application, we should not write query for each pod or container. We should write one single query. It will return for us one single value, regardless of where our pod are and which node is executing them. And finally is the hardware architecture independence. What I mean by this, that means that the power monitoring tool should support different hardware vendors and different hardware types. For example, CPUs, GPUs, and also CPUs from different vendors like Intel, ARMs, and so on. So in the literature, there is actually a few projects that can actually cover most of these requirements. And one of them is Kepler project. So just to give just a brief introduction of what is Kepler. So Kepler is a power monitoring tools that is dedicated for Kubernetes and OpenShift actually, but is designed firstly for Kubernetes in order to report power at the container level, and it's very lightweight. And also the community supported a lot. Now we have actually 2,000 contributors and almost 1.4K as a CNCF GitHub project. And actually, this project is starting by Red Hat and IBM at 2022, and then is incubated as a CNCF sandbox just 1 year later. So based on my evaluation, I see that Kepler supporting most of all the requirement. And just to give also brief overview about its capacity. So Kepler actually supporting the different orchestrators, as we said, for example, OpenShift and Kubernetes, and also supporting a different CPUs and GPU and RAMs. And in the matter of the multi-domain power reporting, so Kepler right now supporting just the CPU, GPU, and DRAM power, but the storage and the network and the other accelerator are now in the roadmap of Kepler, so they will be sooner supported. And Kepler have also the capacity to report the power by fine granularity. That's a process, then a container, then pod, and after that, after pod, of course, we can aggregate to the namespace. So actually, how Kepler is work? So the principle is simple. We have a power monitor. We have a power monitor, the bare metal power monitor, or even in the case we are in a VM, so we have a machine learning model that will estimate the power. And this total power of the compute node, it will be used in order to divide it among the container that they use this power. Just to give a simple example how exactly it's working. So imagine that we have a compute node consuming like 60 watts. So there is an idle watt, for example, 40 watt is just idle, just to keep this compute node on. And there is 20, which is the active power that use it to run the workload. So Kepler first trying to track the CPU usage for each process, regardless of the deployment unit, whether it's inside the container or standalone VM or so on. So first we see the CPU usage of each container, and then aggregate the CPU usage per deployment unit. For example, for the process 2, process 3, they are in one container, so we will aggregate that. And after that, based on the CPU usage, we will derive the power consumption. So for example, if we have a process consuming, for example, 10% of CPU usage, so that's approximately consuming 10% of the power. So this is the principle how Kepler is working. So this is just simple example showing you how we can derive the power of the container using the CPU usage. But the question that we always ask at the community, whether at CNCF Kepler or other, is to which extent Kepler is accurate, because we do know that it's supporting a lot of features. It's very awesome in the way how we install it. It's very worthy as tools, but we never assist its accuracy. And why is it challenging in order to assist the accuracy of container power monitoring tools? Because we don't have the ground truth. We cannot compare what's Kepler reporting with a power, like with a power meter at the container level, because we cannot do that. So in order to answer this question, I have dedicated some research time in order to investigate the problem, and I find out, or I finally achieving what I call an accuracy validation framework for container power monitoring, which is first of its kind. this framework is used to validate the accuracy of container power monitoring tools. So the idea is very simple. The idea, first, I have to create an isolation environment. And this isolation environment, I will be sure that the power reported by the node, it will be the power consumed by the container. I will detail the isolation environment, how we create it. But this is the idea of the framework. And then in this isolated environment, I will make one containerized workload. For example, here I make a web service. And then I measure the power before starting the traffic and after starting the traffic. And I measure the power by using Kepler as a tools under the test, and also measure the power for the entire node, which will be equals to the container consumption. And I compare these value and I see to which extent the Kepler is accurate, for example. So just to have an idea about how this environment isolation setup is created. So first, I have to isolate any interference or noise that coming from non-experimental workload. For example, from Kubernetes control plane, or for example, operating system. So anything not related to the experiment should be run in another socket or in another in separate socket than socket running the experiment. And also, the second thing is to like manually and hardly control all the features or all the hardware features that may impact the power measurement. For example, I have first making my container in one exact physical CPU core. And then I disable turbo boost option, for example, to not increase the frequency suddenly, and also disabling C-state, hyper-threading, that's making no other process sharing the core with the process under the test. And also, for example, the swap is disabled also in order to not letting any dispagination or memory caching impacting the power reading. And like this, we are sure that the power that we are reading at the node level is exactly the power consumed by the container. And at this moment, we can compare. And in order to validate the accuracy of Kepler, we create 3 different scenarios, which are very realistic in the cloud environment. So the first scenario is the dynamic core frequency scaling, because we do know that the power manager for the node, it will automatically or dynamically scaling up or down the CPU frequency based on the load of the compute node. So we want to investigate to which extent Kepler is accurate when we dynamically changing the core frequency. The second thing, we do know that like our workload will not run alone in the cloud environment. So there is others, they also running their containers. So we want to see what is the impact of multi-tenant environment. Like, for example, when we add other containers with our containers, is that disrupting or making the power reading not accurate? And the third thing is the CPU idle state transaction, because we do know that at the hardware, we have some mechanism like C-state, which are capable to, for example, shut down some part of the hardware, specifically the CPU core, when there is no workload. So what is the impact of going from on and off to the accuracy of Kepler? So we will detail this scenario one by one. So the first scenario, the research question that we are targeting here is how does the CPU frequency scaling impact Kepler power measurement accuracy? So what we did, first, we have fixed all the features that can impacting the power. For example, fixing the N-core frequency, fixing the CPU frequency for all the other core, putting nothing on the socket, and we have only our web service stressor. And is deployed, is painted to one core, and then we like step by step increasing the frequency. So what we are expecting here, what we are expecting is that the power will be increasing, because we do know that when we increase the frequency, so the number of operation will be increased, and that's mean the power will be increased. But what we see, how Kepler is reporting power, is totally different. So the first observation we can see here is that Kepler is overestimating the power by 15 times. And why is that? Because Kepler trying to distribute the total power just for one container. And since we have just one container on the entire socket, so he assumed that all this power is consumed by this container. And the second thing that we observe here is actually the trend when we increase the frequency, because you can see that this is the real power on blue. When we increase our expectation, that say that when we increase the CPU frequency, the power will increase. But when we see Kepler, when we increase the power is decreasing. And why is that? Because Kepler is mainly driven by or its estimation model is mainly driven by the CPU usage. And if we just making the relationship between increasing the CPU frequency and the CPU usage, we will see that when we increase the core frequency, the CPU usage is actually decreasing. You can see that the CPU usage is decreasing, and also the power reported is decreasing. And this is logical, because when we increase the frequency, so there is more cycle per second. So this is why the CPU is shrink. But Kepler reading that as decline in the power, which is the inverse. And how we think that we can address that, I think we can introduce the CPU frequency as also an attribute in the model in order to estimate power more accurately. So the second experiment, where we want to actually validate like what is the impact of multi-tenant containers on the Kepler reported power. So what we did, we fixed the CPU frequency for all our core and also the N-core frequency, and we start traffic in our web service. And like each step, we added 2 other co-running containers just to see the impact of the multi-tenant containers on our power reporting per our microservices. So what we are expecting here, that we should have no disruption in the power reading, because actually we didn't change the workload of our microservices, and also we didn't change the CPU frequency. But the result is like what we expect is correct. You can see that the power is not changed that much, but the power reported by Kepler, you can see, is decreasing while we are increasing the number of containers. And why is that? Because Kepler, as we say at the start, is trying to actually distribute the total amount of power in one container. And when we increase the number of containers, he tried to redistribute it again. And this is an error. So in order to address that, we think that the power estimation model should be independent of the number of the containers. And just to go to the next experiment. So the next experiment is we are trying to see to which extent that the C state can impact the power attribution accuracy of Kepler. So what we did, we start as usual. We make our stressors, we start traffic, and we fix all the CPU frequency for all the core and the N-core. But this time, we first disable the C state on all the core, and then we enable it only for the core that we are running nothing on. So what we are expecting here, we are expecting that nothing will change. Because actually for our workload, we have changed nothing. CPU frequency is kept fixed, and C-state is disabled, we're running the same traffic during all the experiment. So our expectation is correct. You can see that we consume 2.5, I think, 2.5 like when C-state is enabled, and also 2.5 when C-state is disabled. But you can see that Kepler just is misunderstanding the activation of C-state. He dropped, for example, from almost 11 to 6. So it's almost 50%. And we can see here that the CPU usage is actually not changing during the activation and non-activation on C-state. And we can see here in very detailed way how Kepler is actually see that the drop in the C-state or the activation of C-state is drop in the power of the measured container, which is not true. You can see here the dynamic power is dropped from 12 to 6. So in order to fix that, what I do suggest is to, instead of using very simple model, the power monitoring is very, like reporting the power is very complex task, and we have to include all the metrics and the factors that can impact this readings. For example, the CPU frequency, the number of container within our container or within the socket that running our container, and also the C-state, the activation or deactivation of C-state and its relation to where it's activated, whether it's in the core running our process or the others. So finally, to conclude this this presentation, I rather prefer to say to make a call to action rather to making conclusion. But what we see here that actually yes, Kepler is overestimating the power container and have some error in reporting. Also, there is, for example, there is the support of GPU and ARM is still in early stage, but Kepler, I think, is the most powerful tools and most promising tools that we have. And yes, its accuracy is maybe a little bit overestimating, but it still need further improvement and refinement in this area. And the message that I want to deliver to the Green Think Summit here, we still need your help and your involvement, and we invite all the members and the audience of Green Think Summit to actively contributing to Kepler. And also we do have another CNCF tag for environment sustainability. So you can reach us in these two community, and any feedback from you regarding sustainability effort or power measurement will be welcome. So thank you so much, and if you have any questions, I'm available offline.
Hello, everyone. I'd like to talk today about two hemispheres with one composite mind. To get into this, first we need to discuss what is an agent. And to me and to many people, an agent is anything that can perceive, can decide, and can act. And what it perceives is an environment, and what it acts on is that same environment. But it also has to make some decisions, but it needs to have agency or autonomy to be able to act on its own authority. So perceive, decide, and act. That's what many people think is the definition for an agent. But in today's language, many people, other people are currently using the term in a much more specific case. They think, well, if you've got an agent or if you're agentic, you have to have some large language models in there somewhere. You have to have multiple agents in there, and it has to be learning about something. It has to learn from its historical experiences. So there's these two definitions of agent going on. I think the only absolutely required ones are the first three here, but a lot of people would probably disagree and say you need all six. So the two hemispheres that I'm referring to here are both cloud and edge. Those are the two halves, and we're going to build systems that include both of those elements. And why do we want to do that? Well, because it's a much better, much more sustainable solution in many ways. Large language models have lots of parameters. They take lots of compute to run all those parameters. That compute requires energy. That energy produces heat. You have to cool that heat. So large language models are nice and they do amazing things, but in many cases we can get by with small language models. And so they have less of a energy footprint than the large language models do. We're also going to talk about traditional AI algorithms. And those algorithms today, in many cases, can give you guaranteed optimal answers that the language models cannot. And they can also, in many cases, require less compute power to do it. They're not as flexible as the language models, but if the task you need to solve fits what they can do, that's probably a better solution right there. And again, we're reducing energy, we're reducing heating. AI, of course, is good for many things. If you can make precise measurements and recommendations, well, that's going to lead to less waste in the environment. You're going to use less water. You're going to use less pesticides. We already talked about how the language models are very energy hungry. And the cloud, even just sitting idle, takes a lot of energy. If we move things to the edge, we're going to have a lot lower footprint for energy. If some edge solutions now send everything to the cloud. Well, if you don't have to send every byte to the cloud, that's less communication costs. And then there's the whole energy savings on the whole communication pathway. Cooling is a very large part of many data centers today. It's a substantial fraction of the energy that they consume. With an edge device, you can probably get away with ambient cooling, so there's no cooling itself involved. And of course, edge devices have much lower latency because you only have to travel to the other side of the board to get your answer, as opposed to going all the way to the cloud and coming back. One of the features that I believe we're going to see in the next few years is the adoption and the rise of, some people call it composite AI. To me, it has three elements to it. It's multi-agent, it's multi-tool, and it's multi-AI. A lot of people are already doing multi-agent, multi-tool designs, and that's not particularly new. What I do think is new is the multi-AI piece. Too many people are ignoring the capabilities of some of these traditional AIs, and they don't do everything, but they should be used where they have been designed to be optimal. So large language models are one kind of AI. We talked about they take a lot of parameters and a lot of energy to compute. Small language models are also a good option. They help reduce your energy footprint, and many of them can run, some of them can run on the edge device, but there's a whole lot of other traditional AIs that can be employed. And like I said, in some cases, they're a better solution. So I want to talk about a few different ways to arrange how agents interact with each other. And the first thing I want to say here is that I'm using these hats here as agents. Each hat is one agent. The hats themselves don't really mean anything in particular here, but I'm just using different hats to represent that these different agents have different roles to play in whatever we're doing. And the icon here, the gear icon, that's about a process. And a process is either one or likely a small number of agents that are working together to perform some kind of a task. So that's the icons I'm using here. So in the programming flow, it's the architecture that is deciding how agents talk to each other and what paths they can use. You can code them that way, and that's great. It works in many cases. Another somewhat more sophisticated idea is the idea of orchestration. And in this case, we have some initial agent. Here I've got the cop's hat in here, and the cop looks at it and decides which of the three agents below should he pass this information off to. Is it primarily about healthcare? Is it primarily about something else? And he will pick the agent that is executed next. So in orchestration, one agent is really deciding how to control the flow. A somewhat more sophisticated and subtle version is where the agents decide among themselves, and each agent decides for itself which other agents it's going to communicate with next. This is called a choreography. And each agent is deciding how to flow messages around. The choreography is a nice idea. It's very flexible, but it's also very challenging to debug. So if you're just getting started, I would recommend you stay with more of the programming or at least the orchestration. Save choreography to when you're more comfortable with all the things that are going on here. So let's talk about a number of patterns. One of the patterns that I really like is called deterministic core and probabilistic border. Yes, I know that's kind of a mouthful, but let's just kind of step through it quickly. So let's suppose that we have some process and we can use a traditional AI algorithm to do that. So maybe it's a classification, maybe it's a regression, maybe it's something else. But what's really happening is we have structured information coming into it and structured information coming out of it. The algorithm itself is deterministic and it's working on structured information. And that's nice. You can often get optimal answers out of this kind of a solution. However, the world is a noisy and messy place. So if you've got noisy text, noisy image, noisy videos, traditional AIs have not been very good at dealing with these kinds of messy inputs. So we have these unstructured things coming in, and we're probably going to need to use a probabilistic algorithm to even make sense of what's going on. And the goal of this agent is to convert from the unstructured, messy world into a structured, more normalized sort of a world. But then he's creating the symbolic input that's going to go into the traditional AI. If we're in a deterministic core, we can do other things as well. In this case, we've added a rules engine to take and look at some of those symbols and make some determinations. This is a deterministic algorithm, but we're in the symbolic space, in a structured space, so we can do systems and build them like this. This is actually the structure and architecture for a system that I've been recently working on. We use LLMs to process the messy text input, and then we do a number of deterministic algorithms to figure that out. And then finally, we didn't do this in my project, but we easily could have. If you have these symbolic outputs, structured outputs from the cap there, you could go back into another probabilistic algorithm to fluff it back up into nice text, images, videos, whatever you want to do. So the idea here is that in the core of this, we want to use deterministic algorithms. And part of the reason for that is they don't hallucinate. You can be sure that what's going on here. But on the core, to deal with the real world, the messy world, we need to put some probabilistic elements to deal with that. One point to notice here is that if the input probabilistic algorithm messes up, we can see it by examining the symbols that it's output, and we can control what's going on. We can ensure that the probabilistic algorithm is doing what we really wanted it to do. We don't have to worry about, the rest of some other LLM trying to figure out what's going on here. Let's talk about some data flows here. If we have just, call return, that the main program calls agent 1 and gets the data back, and then it calls agent 2 and gets his data back and passes it on, that's certainly a way to do programming. We've been doing it for decades. If you've only got a single processor, this might be the one that you want to choose. But if you have multiple processors, and particularly if they run at different rates, what you might want to do is a more asynchronous architecture. And in this case, we would be using queues, perhaps MQTT kinds of queues, and agents read from their input queue and then they write to their output queues. And this just gives a little bit more flexibility to how the agents are running. Timing issues become somewhat less important here, less hard to debug. Another version of this is you might want to put some state spaces into the message flows. And why would this be a great idea? It's a little subtle, but if you have a state stores like this, you know who wrote that record. And we also know who's reading those records. So it's a little bit easier to reason about what's going on in the flow, and it's a little bit easier to debug it. So again, some of these are not that radically new ideas, but there's different ways to approach how the agents are going to communicate with each other. Another approach, of course, is that we want to use detailed computations, intense computations up in the cloud where we have the compute resources to do that, and we have the data storage resources to store all the information that we want to process. Down on the edge, you don't have as much compute, you don't have near as much storage, so you might run similar algorithms down there, but you're probably only going to get more of an approximate answer. So why don't we run everything in the cloud? Because the cloud can be intermittently connected. The communication lines might drop between the edge and the cloud from time to time for various reasons. But on the edge, it's always on, so that's really nice. So that's another set of reasons for why you might push one agent to the cloud and one agent to the edge. This is another design pattern that I really like. It's called the designer checker. So we have a designer agent, and this could either be a large language model or it could be a human, and it's designing an algorithm. It's producing a version that's supposed to satisfy all the constraints. Now, LLMs hallucinate. People get tired and they make mistakes. So what is generated may not be quite right, but it is a full design. So that output then goes to some checker algorithm. And in many cases, we would like the checker to run some deterministic algorithms to make sure that the output generated by the designer actually satisfies a number of the different requirements that we have. And this could either be from equations or some symbolic system. And that's a great way to make sure that you don't have any hallucinations left in the designer's output if possible. And that only really works if the designer's output is structured output. If the designer's output is unstructured, you're not going to be able to use deterministic algorithms, but you might imply a different LLM to check the results of the first one. This isn't going to guarantee that you don't have any hallucinations because the LLM judge could also hallucinate, but it reduces the chance that the hallucinations are going to get through. So I really kind of like this. And I would mention that you might want to say, well, let's just make the checker a tool. I recommend against that because the designer could decide, I don't need to run this tool in this case. And so you lose the advantage of the pattern altogether. If you do it with one of these programmatic kind of situations, the output of the designer must always go through to the checker. And so you get some assurances that way. This one is a little bit more about fault tolerance. So let's assume that this graduation cap agent is up running in the cloud and he's doing some deep forecasting. He's got all the compute he needs and all the storage resources he needs, but the communication line drops for some reason. So the best data that was flowing down to the edge before now isn't flowing down for some period of time. On the edge, you could say, well, what I'm going to do is I'm just going to use the last best estimate that I had, and I will continue to do that. But if there's a period of time where that's going on, you're still using data that's stale, and it's getting staler and staler and staler. In some cases, you might be able to have a simple agent on the edge, this simple forecaster. He's not as good as the one up in the cloud, but he can project data forward a little bit. And so if you use this pattern, this simple forecaster is looking and saying, hey, I didn't get any input from the cloud. I'm going to do my own forecast, and I will keep doing that as long as there is no information. But as soon as I get information back connected to the deep forecaster, I'm going to switch and start using his information, and I'm going to update my own tables so that I know where I'm actually at. So this is a way to add some kind of fault tolerance to your system. So there, we've talked about the agents, but now let's look a little bit about some of the processes. Again, a process here is one or more agents, but they do some kind of recognizable human function. But you might have one process that has to run before a second process. This is just a sequential relationship between them, and you can diagram it in this way. Some processes can run in parallel. They don't have any interaction with each other. You can launch them both, and they go off and they do their things, and everybody's happy. But there are cases where you have a couple of processes, and they share something that can't be shared. So let's say that these two processes need to share a piece of hardware to do something. Only one process can use the hardware at a time, so these are exclusive. You have to make sure that only one of these processes is running at a time. And then, of course, you might have multiple processes running, particularly from the parallel case, and you need to merge them back together. Not a huge idea here, but these are some of the dependencies to think about and probably to design out as you're doing your architecture. So we've talked about agents acting. One of the key ideas is, do we want the agent to act? Do we allow the agent to act? Do we allow it to have agency? Do we allow it to have autonomy to work on its own? So you get to these decision points where the agent has to make a decision to go left or go right or do A or do B. Do we give the computer agency to make that decision on its own? Or do we say, no, we need a human to make this decision? And in any architecture, you're probably going to have a lot of different decision points. Some of them you may give full autonomy to the computer and say, yes, I want you to make the decision, but other more carefully considered ones require human agency to make that decision. So this is all about putting agents or humans in the loop. So the human's job in this thing is to validate or review what the agents have done before it, to approve it, to maybe actually guide what's going on. And this is just getting us into the whole idea that the agents of the humans are collaborating together. We want to give some agency to the computer so we don't overwhelm the humans, but at certain points we want the human to be involved and to take control. So we've talked about a lot of patterns. Let's now look at how to apply some of these patterns, certainly not all of them, but apply some of these patterns to a precision agriculture application. So the first thing we're going to do is we probably want to look at the weather system, and this is the macroclimate idea. We're going to need that information to make some decision. We want to look at the microclimate. What is the soil moisture? What's the temperature? What's the pressure? What's going on there? That's information that we're going to need. And we're going to assume that we have some drones out there and they're flying around our crops and they're providing us video data or image data, and we want to take that as input as well. These agents are basically doing nothing more than perceiving what's going on in our crop environment. So they're just part of the perceive part of the agent system. Next, we want to make some decisions on this data. Well, one of the things we probably want to do is look at the crop health. And we're going to assume here that the crop health is based on the microclimate, how much soil moisture is out there, what's the temperature, that sort of thing. And then what is the information that we're getting from the drone? Are the leaves green? Are they brown? What's going on that way? This agent, this process is helping to determine what the crop is doing. How does that really look? We also probably want to capture history on everything that's going on here. And we want to capture that so we can look back in the future and make and understand and learn from that data that we had. So we probably want a history agent in here. This may not be a full agent. It may just be a database or a knowledge graph, something like that. But we probably want to capture that as well. Now, in this particular picture, I'm showing a single planner agent, and this planner is orchestrating the entire operation here. That's an easy way to do it. In some cases, it's easy to conceptualize what's going on, but the planner has a lot of work to do, and that is one of the reasons that you might want to split the planner up into multiple different components. But you really need to be looking about exactly what each of these components are doing. After the planner, well, we probably want to do some yield prediction. How is the crop progressing throughout the entire growing season? Is it doing well? Is it doing badly? What do we think we're going to get at the end? And of course, this is based on the current crop health and also the history that we've had from past runs. And maybe there's some compliance and reporting going on, so you probably need to do some of that. But we also, the planner is helping us determine what we need to do in the next state. And one of those things is, do we have to irrigate? What is our irrigation plan for the next period here? Also, what do we want the drones to do in this next period? Do we want them to fly at all? Do we want them to collect specific kinds of data? That's all part of the decide step. But then the final action for this entire macro process is we want to take this general irrigation optimization plan and we need to actually implement it at the detailed level. And so that's what the irrigation control is doing. And we have a plan for the kinds of things we want the drones to do, but somebody's got to figure out how to navigate those drones up and down the crop rows. And so that's what this drone navigation is all about. And then, of course, finally, why are we doing the drone navigation? So that we can now collect video in the next period about the drone. So we've got some feedback loops going on here. So like I said, this doesn't employ all of the patterns that we've talked about. Some of them would be buried inside some of these other processes. But this is a way to kind of think about how you would do a multi-agent system, a composite AI system for a particular industry, in this case, precision agriculture. So just to wrap up here, I just want to make, a couple of more points here. Composite AI, I think, is going to be growing in importance, particularly in the next 2 to 5 years. It's about being multi-agent, about being multi-tool, and of course, being multi-AI. I think too many people are ignoring that element. There's so many kinds of artificial intelligence and machine learning out there. Too many people are ignoring a lot of those. And if you're designing only with large language models, I think you're probably wasting energy. You're probably using bigger hammers than you actually need to use. So we've covered a lot of topics here. There's many other details that I would have loved to go into, but don't really have time here. But if this has given you some ideas, it's given you some questions, I'd happy to connect with you and dive some deeper on some of these issues here. The QR code here is a link to my website at which you can contact me. Thanks for your attention.
Hello, everyone. You're watching the Green Things Summit, and this session is From Waste to Sovereign Energy, Renewable Natural Gas in an Unstable World. I'm Tiffany Nielsen, and joining me is Dr. Maureen Kinua, and she is the founder and sustainability advisor of Prof. Kinua Consulting. How are you today, Maureen?
I'm pretty good, Tiffany. Happy to be here. How are you?
I'm excellent. Thank you for asking. And to start us off, can you break down what renewable natural gas actually is and how it is produced from everyday waste streams?
Right. So, renewable natural gas, I'll call RNG in short, is a gaseous fuel that's derived from organic material. So, it's from sources that can be renewed. So it is a pipeline quality gas that is that's fully interchangeable with fossil-based conventional natural gas. So the way it's produced is there's two ways. The first is a biological process that's known as anaerobic digestion, where microorganisms take that organic matter. So it can be livestock manure, it can be landfill gas, it can be food waste. They take that up and convert it to methane. Another method that's not widely adopted is thermogasification, where you take, cellulosic crops like grasses, forestry waste, ag residuals, things that can be broken down pretty easily. You burn those up to produce methane. So once that methane is produced, you clean it up to meet the natural gas pipeline quality. So that means bringing it from like a 60% methane to about 95 to 99%. So you're removing moisture, you're removing CO2, you're removing oxygen, nitrogen, any contaminants that would otherwise, impact an engine.
And what are the most compelling real world examples of converting wastewater, food waste, or agricultural byproducts into RNG for practical use?
Right. So as of last year, the end of last year, there's about 570 operational facilities in the United States and Canada. California has about half of those, so 230 something of them. And so California provides a pretty good case study for how we can adopt, converting different waste streams into RNG. So about 99% of all heavy duty trucks, so think of the trucks that are transporting your goods from point A to B, the trucks that are picking up trash, those kinds of trucks, 99% of them in California that run on natural gas are actually using renewable natural gas that's come from wastewater, from landfill, from food waste. So this intensity in California is actually driven by the state's low carbon fuel standards. So this is something that has really incentivized cleaner fuel alternatives. Someone that's producing high carbon can buy those credits from someone that's producing low carbon.
Interesting. And in real world projects, how critical is the ability to use existing natural gas infrastructure for RNG? And how does RNG's reliability and dispatchability compare to other renewables?
Right. So that's something that is one of the attractive things about renewable natural gas. So using the existing natural gas infrastructure that we're using for fossil-based natural gas can really help accelerate RNG adoption, because all you need to do once you've produced the biogas is clean it up and make sure it meets the quality that's required for pipeline and inject it into those existing networks. And of course, as far as infrastructure for vehicles, for example, for RNG vehicles, again, as long as it meets fossil-based natural gas standards of 95%, then it's again, it's the same gas, just the source, instead of digging it from the ground, you're producing it from resources. So yeah, RNG projects can easily, plug into pipelines, the storage, the end-to-use equipment, like I mentioned, with the vehicles already in place because it behaves the same as conventional gas once it's been cleaned up. Um, and the good thing about it, you asked about reliability and dispatchability, is that once you've cleaned it up and you can inject it into regular storage infrastructure, you can deliver it 24/7. So it's on demand as long as you have the feedstock, right? As long as you have cows producing manure, you have people wasting or throwing away food scraps, then you're able to produce this. So that's where it differs from things like wind and solar that are inherently weather dependent, right? You get solar if it's sunny, you get wind if it's windy. So their input, wind and solar, has to be forecast and paired with a separate storage system, and those can be quite capital intensive. um, and so in terms of reliability, you're depending on the climate or the weather versus RNG that's there as long as you have access to the feedstock.
That's great. I think it's amazing that waste can be renewed and turned into renewable natural gas. It's very exciting.
It's only wasted if you waste it.
Very true.
Yeah.
And how and where does RNG fit best within a broader decarbonization strategy, supporting both climate goals and community needs? And where might
Mhm.
it not be the right solution?
Right. So RNG is not a universal replacement for all the fuel. So RNG is best reserved for hard to electrify uses. So think again, heavy duty trucks, where putting an electric system for a heavy duty truck or some industry processes just does not make any sense whatsoever. So that's where RNG would be a very good alternative to fossil fuels. Um, in the case of like a passenger vehicle, your everyday vehicle, your small vans, electric vehicle will certainly beat an RNG engine on efficiency, the infrastructure cost, and the long-term decarbonization value. However, what I will say to that is you can still produce electricity from RNG. So you might not need to turn passenger vehicles into RNG engines, so they can still be electric, but that electricity is coming from RNG. So the end product can be RNG, or you can take that RNG and turn it into, or biogas and turn it into electricity. Also, in places like, large land, places without landfills, places without livestock waste, that becomes uneconomic, right? Because you're not producing the feedstock. There's no point in installing that. Where RNG thrives in our quest for decarbonization is that it reduces greenhouse gas emissions by leaving that fossil CO2 underground. So think of RNG as a recycling carbon system. So instead of digging up new carbon by digging up new fossil based natural gas or digging up new fossil petroleum, you're leaving it where it is and using plants that had already pulled CO2 out of the air as they were growing, right? The whole process of photosynthesis, they've already taken in that CO2. All you're doing is turning that organic material that's already embedded in the plant into biogas and then RNG. So you're releasing the same carbon, you're not adding new carbon into the atmosphere. So that's the big point about RNG when it comes to decarbonization. And then just to add one more thing is that, if we leave the livestock manure on the farm just sitting there doing nothing, or the food waste in the landfill, we're leaking that methane into the atmosphere, which is, a pretty powerful greenhouse gas. And so by capturing it, we're really helping to decarbonize our environment.
Thank you. And that leads us into my next question. Methane reduction is a big part of the RNG story. Can you explain why that's so critical from a climate perspective?
Right. So, like I mentioned, methane is a pretty potent greenhouse gas. And globally, methane is accounting for almost 20% of all the greenhouse gas emissions. In the US, it's about 12%. So, of this, the human caused methane from livestock is about 30%. Landfills come in second. Again, when that food waste is just sitting in the landfill, going through the same anaerobic digestion process, we're releasing that methane. And also, our wastewater treatment processes do produce methane. So, why methane is such an issue is that when you compare it to carbon dioxide, it captures a lot more heat. So, if you had 1 ton of methane, it traps about 80 times more heat than 1 ton of CO2. So, if we can cut down on the methane, then that's really a fast way of slowing down. Um, the warming effect and just climate change in general. So what RNG project, why they matter, RNG implementation projects, why they matter is because they capture this methane again from waste that would just be sitting there, releasing methane, leaking it into the environment. Instead, we're taking it and turning it into a renewable energy source. And also diversifying our energy sources, right?
Absolutely. And
Mhm.
beyond emissions reductions, what are the strongest business and economic reasons to invest in RNG, including new revenue and cost savings opportunities?
Right. So beyond the emission issues I've talked about, RNG can be a cost center. You can turn something that is just leaking money, like a landfill that's just treating waste, a wastewater treatment facility, or even a farm that's just utilizing resources. You can turn that by monetizing your waste stream, right? Because now you're selling the RNG. And you're also possibly selling the carbon credits to a high carbon producer. So you're reducing the fossil based gas or diesel or petroleum. And if you're a farmer, for example, and you get like a long-term fuel contract with someone, like maybe you get a contract with a city, like I will provide you with the RNG that you need to run your school buses and your trash, your pickup trucks and all these things. That's monetizing your waste for a farmer for something that was just sitting there, right? So you can think of landfills also selling their RNG. Food waste that was just sitting in the landfill can now become a revenue source. Also, besides emissions, in terms of business, we're thinking of this as a sustainable waste management alternative for something that we're running out of space. So we're running out of space for waste to go into landfills, right? We don't have barely have enough land already for people to live in, let alone for trash to just sit there. So by creating RNG projects, we're creating local economic development along the value chain. So think of the construction jobs that would come up for people that can work in installing these systems, the equipment that needs to be manufactured, the mechanics that can take care of these new RNG cars, the people that have to maintain these operations, and especially in rural areas that need an injection of revenue, I think that would be a much needed investment.
For sure. I couldn't agree more.
Mm-hmm.
And in an era of volatile global fuel markets, how does locally produced RNG reshape energy security and long term costs for communities and companies?
Yeah. So think of locally sourced RNG as decentralizing your energy. You're able to produce your own energy, right? Because you, even where you need electricity, all you need to do is convert that biogas. You don't even need to take it all the way to RNG. Once you've produced that biogas, you can take it to electricity, and that would be decentralized electrical production. So that would be homegrown fuel that's not tied to whatever is going on globally. The global oil and gas shocks due to different reasons, which again strengthens your own energy security. And then it's stabilized, it's stable, it's not dependent on what's going on um, internationally or locally if you're able to produce your own fuel. Also, again, I mentioned this when you think of those long term RNG supply contracts, you can hedge fuel volatility and then combine that with federal and state credits. Then you're able to really provide low cost, predictable per mile resource versus, if you're using diesel, for example, you can't have that predictability of how much it's going to cost you per mile for, again, the heavy truck users. For those high mileage, energy intensive users, you're giving them a stable price and it's predictable what it's going to be. And unlike wind and solar, again, the production of it is stable.
Right. Okay. And what simple framework or first steps can leaders use to spot strong RNG opportunities in their operations or region and quickly assess whether an RNG project makes business sense?
Right. So if a leader came to me and they wanted to know, does RNG make sense in my region? I would advise them to approach it from a three-step process. So the first thing would be, do you have enough reliable organic waste? In your area, do you have livestock farmers? Right? Do you have cows, swine? Those are usually the best, cows and swine, because just volume wise, do you have that? Do you have food waste? Do you have a food waste collection program? A lot of states these days do have those. Not every state, but quite a few have a food waste collection. What are you doing with your wastewater, the solids that come out of your wastewater? Are you just sending them to a landfill? In your region, do you produce landfill gas? So once we've looked at what your organic waste landscape looks like, then we can see what your footprint would be to support like a 10, 20, 30-year project. The second thing I would look at is, do you have the facilities, the fleet to actually use the RNG, right? Do you have a nice fleet of vehicles, police cars, again, like I said, transportation, delivery trucks, waste pickup trucks, school buses? Do you have a fleet that will actually use your RNG? So that would be the second thing I would look at. And then the third would be, what are the federal, um, state, and local policies and incentives? The low carbon fuels, for example, that's something that's really pushing RNG adoption in California. Do you have it in your region? Are there any grants that are looking at decarbonization that you would qualify for? Are there any interconnections where you can easily inject the RNG into the natural pipeline. So those would be all things that I would be asking you. So do you have a reliable organic waste source? Do you have the facilities that will actually use it? And then do you have any policy and incentives that would actually help build a viable business case? And again, the goal for those policies is usually to bring the price down. So this is usually exactly the kinds of conversations I have with stakeholders. Like I offer technical and advisory support to evaluate the feasibility of these opportunities and see if it's something that would fit to work in your region.
And I know that we didn't discuss this question, but I am curious. How long has RNG been in production for? And are there other countries that have been using it for a longer amount of time, or is this just new to the US?
So the process of anaerobic digestion has been around since forever, and I do mean that because without getting too much into the biology, but the microorganisms that actually produce methane were the original microorganisms here on planet Earth until the oxygen producers took them over. But that's like back. The adoption of RNG is not something it's not something new. It's been used traditionally in, many African and indigenous communities that took manure, you put it in a container, you produce biogas, you use that for heating. It's not something new. The only new part now is, turning it into electricity, turning it into a fuel that you can use in an engine. In terms of adoption compared to other countries, I would say countries in Europe are probably further ahead in adoption of RNG compared to the US. I think it's not seen as the most sexiest fuel source. It's all about electricity, but it has a lot of potential. And again, as people are looking for alternative and that energy independence, there's more conversation around it now.
And for all of our viewers, if you're using RNG in your country or if you've heard of RNG, let us know what your thoughts are on it. We'd love to hear from you in the comments. Now, another question for you. Looking ahead, what role do you see RNG playing in the future energy mix over the next, say, 5 to 10 years?
Right. So over the next 5 to 10 years, RNG's role in the energy mix will be shaped by feedstock and the technology itself. So, waste streams, as we collect more of that food waste, as we collect more manure, as more states and communities start requiring stricter laws for the emission of landfill gas, the waste stream will continue to scale. Um, the newer path of thermal gasification, if you remember, I mentioned two paths. Anaerobic digestion is more of the wet stuff that uses microbes, and then thermal gasification is where you burn more drier, harder to break down residuals and energy crops. So thermal gasification is not as adopted right now, but if that pathway grows with time, then that will help to really have a meaningful volume of RNG past, 2030. So a recent study in the US showed that, if we were to collect about 45% of all the biomass that's suitable for bioenergy, right? So there's a lot of it available, but it's not like we're collecting 100% of it, right? But if we were to collect even just 45% of it, it would take another 10 to 15 years to reach an RNG production that could meet the commercial energy needs we currently have. So again, RNG is great. It's not a solution for everything. It does really well in decarbonizing heavy duty transportation and hard to electrify loads within the existing gas infrastructure. We don't need to build new pipelines, new vehicles per se for it. We can use what is already available. And, California is a demonstration of how RNG can deliver these carbon negative outcomes, especially for trucking. And it also shows how policies like the low carbon fuel standard in California can really drive the industry to produce more RNG volume. So, all in all, looking 5 to 10 years for now, I see most of the investment and public funding flowing into RNG facilities that serve fleets, heavy duty fleets. So, think of those big trucks. Wastewater utilities is another one that's certainly going to grow, especially within the next 5 years, as a lot of wastewater facilities need to be remodeled, um, and large waste generators. So, and so that's where, I want to really focus my work, supporting organizations to identify those high impact niches so that their RNG projects, are bankable from the planning to the design, construction, and actually implementation.
Now, Maureen, can RNG be used for data centers?
Yeah, it can, because if a data center needs electricity, you don't need to even clean it to turn it to RNG. You can just use the biogas to convert it to electricity. In a combined heat and power system, you know, you provide heat and power by just running the biogas through a turbine, a combustion, and you produce electricity.
And I have one last question for you. Considering the title of this session, what does the term sovereign energy mean to you?
Right. Sovereign energy means the idea is talking about decentralized energy. So being able to produce your own energy and not relying on external forces, the global oil and gas shocks. That's what I meant by sovereignty. Sovereignty meaning independently producing your own energy.
Well, this is definitely a great time to have this conversation.
Yes, I know. Now RNG can become sexy again.
Right?
Yes.
Well, Maureen, thank you so much for joining us. And to everyone watching, stay tuned because there are plenty more sessions to explore during the Green Things Summit. Have a great day and enjoy the rest of today's sessions. Thank you, Maureen.
Yes. Thank you.
Bye-bye.
Bye.
Good morning, everyone, and thank you for being here. I want to start with a simple thought. Many companies are still trying to manage carbon after it has already happened. They measure it, they report it, they summarize it, but by the time it happened, the machine has already ran, the fuel has been consumed, the window for the changes has already happened. So, my question is, how do we explore and identify the carbon reduction happening in real time rather waiting for the report? My name is Sundar Subramanian. I am part of Cognizant IoT and sustainability practice. As a director, I lead the consumer goods and retail vertical. So, what if it began in the moment the machine decides how to run? That's a shift from an energy intelligence to a carbon intelligence. Energy intelligence tells us what we have consumed. Carbon intelligence tells us whether we should have consumed it in the way, the moment, an equipment is functioning, the conditions are specific to the function of the equipment, and whatnot. Especially for the industries which are leading with heavy equipments and factories, This shift is enormous because in a plant, emissions are not created by abstract policies. They are created by real operations, especially those heavy equipments such as the boilers, the conveyors, HVAC system, the assembly lanes, and many other high intense energy processes that consumed in various stages the way our workloads are being defined in our factories and warehouses. And those moments happen every day. And if we see them, we can predict them. And if we can predict them, we can influence them. And all this also can happen at the real time. Then sustainability does not stop at the report, after the report. In fact, it can become part of your operational capability. That is what I mean by a living system, which I will talk about in a bit. A living system that can actually sense, learn, adopt, correct continuously. This is what I wanted to walk through today. And let me start with the problem statement. I often describe the carbon strategy in many industrial environments like this. It's like trying to steer a ship by looking at the wreck it created behind. You can always understand where it has been, but you can never predict what's obstructive next. That's exactly what I want to talk about that happens in many organizations. The first issue is the decisions are actually made after the data arrives. By the time the Scope 1 and Scope 2 emissions are reviewed, the decision window is closed. The equipment has ran, the carbon is already emitted. We are trying to go and prevent that something should not happen in the future while we are not looking at how can we solve it while we are operating it. The second issue is many times the averages hides the truth, right? While a monthly report for any site of a factory may look efficient, may look working well with less carbon emission, but buried within those monthly reports, you may see a repeatable pattern of startup spikes or a badly sequenced load of activities and workloads, or often the carbon intense operations are piled up in a very short moment and a short duration. Identifying those patterns becomes very critical. Those are not hidden in the average reports. Those are all in the individual data points that we can gather. The third issue is where the feedback loop for operations, right? The data might reach the ESG team. They might be able to bring it to the finance and leadership to analyze what has happened, but it did not reach the asset to tell what should happen. That's approach that we wanted to take. Let me give you a practical example. Imagine there are two production lines running two different locations, same output, same kilowatt per hour, but one operating in the cleaner energy consumption window, while the other one is at the dirtier window. The traditional report may look the same by giving the analysis of the energy consumption and the other pattern same, but from a carbon perspective, this looks very different to each other. And if your operating model does not tell the difference, then the carbon strategy is almost retrospective. It's very useful for the compliance and other reports, but it's not enough for the edge and the factory assets to have a decision-led approach for the carbon reduction. So when you say carbon strategies fail, it literally means that your carbon strategies are reacting and too late for an execution. So how do we fix that? We can stop treating a plant like a static environment. We need to start treating plants like a living environment where it starts with sensing, learns by itself, adopts, and also does it correctly. Now let me break it down. First, sense. You cannot manage what you can't see. And in most plants, what we see is still aggregated. We see the facility, we see the lines, but we do not see the actual behavior of the individual asset that is driving the carbon pattern. So we should start instrumenting at the asset level, such as the compressors, the boilers, the conveyors, the CNC lines, the chillers, motors, etc. We stream every data of these equipments, the energy consumption pattern, convert those into a context of the state, the process, the load, the vibration, the temperature, and various information that these equipment and assets give to us. That's where we are sensing and learning first. Number two, start learning. Once you have all the signals, bring in our AI intelligence where we begin to identify, not at all asset level, but at each asset level, how the consumption pattern is, what are the changes happening while we are increasing the load, reducing the load, and also comparing it against the time window. Because a compressor running 15% hotter not necessarily means it is just within the normal range. That could view the industry standard. But a normal compressor that's running in your environment may differ from a temperature control perspective, which needs to be specifically identified and pattern recognized to be able to differentiate whether or not it's running at a normal way. Last but not least, we need to look at adoption. Now, the system is no longer just watching and giving the data and the intelligence and then monitoring it. It's also responding to it. This is where edge intelligence becomes critical because plants do not just need dashboards that explain what is happening and what has happened. We need controllers and equipment and system that can actually help identify patterns, maybe identifying if there is a need to actually stagger the startup. Maybe there is a shift in terms of offloading the critical load of work. Maybe adjusting the set points or the speed of a motor based on the pattern that is recognized that there is a heavy workload coming in. Maybe it is preventing a peak consumption pattern of the dirtier energy window that compounds to a heavier carbon consumption. These factors matters, and obviously the last part is like how do I correct it? A living system improves by itself by bringing all the AI/ML models, understanding the current sequence, previous sequence, and define these changes at the real time and apply it to the devices to adapt to the change. That is what I call it as a living system. Now, let's put this into a manufacturing context. The carbon emission happens in different windows, right? This slide is important because it shows where carbon actually lives within your facility and your factories and where intelligence can influence it at the first. At the center, you have the plant itself. That's the scope one. It's your direct. This is where you are burning your fuel, emitting more carbons because of your assets, and you have a direct control to it. And bringing in a real-time control system can immediately avoid, emissions that are preventable. The scope two, where it is indirect, obviously the areas of your purchase from an electricity side to, components that are coming in from a grid, all those factors into it. So how are we consuming the energy? How are we kind of leveraging the energy patterns? That is the scope two where we can look at and reduce. Then outside the plant, where your scope three, which actually has both upstream and downstream. Upstream obviously includes the raw material, supplier manufacturing, inbound logistics, and whatnot, where the downstream in actually gets into how do you distribute it, how the product is being used, and how it has an end of life pattern, and what we can actually avoid in these areas. Well, in this presentation, I want to just focus on the scope one part of it, which is direct, because that's where the important connection of your asset and the direct emission can be easily controlled. Uh, and in the center of it is the AI plus digital twin, which can actually simulate scenarios, identify patterns, help you out, act faster, better. And why? Because this is where the most strongest operational controls can be directly integrated and managed in your environment. So let's start with direct operations, operational decisions. Then the first step within that is obviously how much and how my electrical consumptions are. There are many other speakers along with me who's going to talk about the optimization on the electricity and whatnot. While this is a common pattern, I probably want to talk about how we create this as a sustainability map, an action map that can actually integrate influence end to end. This one is the very simplest idea in the deck, but also the most powerful one. Not all electricity is equally carbon intensive. And what it means is the timing becomes more critical and becomes a more carbon lever. On this slide, you also will see an idea of a low carbon window where your grids has a cleaner energy and how we are using the cleaner energy consumption window to be able to use your maximum. For example, if I had to say if your grid carbon intensity moves from 12 to 4 p.m., which is heavier or higher compared to other, how are we offloading some of those works which are heavy carbon consumption workloads to be split across the other areas? For example, you wanted to have your boilers heating up the water and having it ready for your operations. Can that actually be happening outside this window? So that heavy carbon emission plus energy consumption workload is being outside the carbon emission window, which is according to the grid, right? That's about the way the pattern we wanted to bring in, and even the smallest percentage reduction could actually influence a higher shift in terms of your carbon emission. That's very meaningful reduction. And the beauty of this model is that it is highly practical for any industry, not necessarily just the factories and the distribution centers, but also expandable for stores, retailers, and whatnot. Because it kind of touch base your various other storage and buffering systems, including a HVAC system. So this slide is simply telling us what is important. It's not about how much power we consume, it's about when we consume. Now, let's think about how do we get this all things together? And that is the important problem every customer is thinking about solving. And with the technology advancements and getting an agentic AI system, it is much easier. Of course, while said that there are three layers of components, one is the hardware side of it, where we bring in the smart EFTs and smart control systems, while an AI model and algorithms which are being built or being bought, which is some of the Scotch products available from the market, and then integrating with your specific architecture and framework solves this problem together. A couple of callouts from providers in this area. There are models built specifically for the energy consumption and emissions from companies like ERM, Cool Planet, and more. And similarly, from an hardware perspective, companies like Schneider Electric and Honeywell and many more have built smart control systems which are enabled with those capabilities such as smart VFDs and whatnot. That brings this muscle for the carbon intelligence for your organizations. Why? Because once you have the visibility and prediction, the next question is how are we going to get this all things together? And this is where we move from the inside to a closed loop response. For example, if I had to talk about a cooling system, do we need to have the fan running at the same speed all day just because that's how it has been configured? No. Answer is no. And same applies to a compressed air system. Do we want it to have our compressed air be shooting out all the pressure that are needed and wasting the energy? Answer is no. And it applies to your pump. For example, do we want our pumps to be running at the full speed where the process demand is much lower? Answer is no. And these are all not these small issues. With this all becomes a daily repeated pattern that accumulates your emissions plus your carbon consumptions plus your energy which is getting consumed more, which means these are also the direct opportunities which are also daily repeatable for your carbon reductions. That is how I see this as an opportunity. Organizations are seeing this as an opportunity, and it doesn't remain anymore as an AI story or an abstract. Well, that being said, what do we do next from here? It's you have to look this up into three different layers: at the site level, at the enterprise level, at the network level. So at the site level, you are able to now look at plants which are able to reduce, avoid emissions. At the network level, you are able to standardize the work and being able to look at a scalable opportunity. At an enterprise level, you are able to connect your operations, engineering, and sustainability all together, while your layers of simulation work, such as digital twin, plays a vital role because it is able to tell you and give you a view of what could be avoided, knowing the patterns. That's more important for us to be able to calculate. With that, let me come to my conclusion slide. So, net zero will not be achieved by just better reports alone. We need to bring in those intelligence to help it happen. especially when organizations like yours have set targets that you want to achieve from and carbon emission and initiatives that are going to help your overall net zero. Here's what I will leave my thoughts with: a three-step approach, having the smart connected assets that are going to help in terms of sense, learn, adopt, and control, which kind of becomes a closed loop with advancements in the edge and AI. Companies like Nvidia and Qualcomm are primarily bringing in those capabilities of doing the compute power at the edge, which can help to have a control process faster to control your equipment and devices. With that, you obviously are able to now do a closed loop. However, the advancement also expands into creating this digital twin where you can also do your simulations such as process simulation, engineering simulation, operational simulation, which kind of combines to say what would be the potential next status and outcome that could be predicted, avoided, and be enabled to be prepared about how do we plan for our carbon emission reduction in the future. These are all the important factors for us to kind of consider how do we bring in the carbon intelligence, the living system that can actually help my factories and facilities run much better faster. With that, I'd like to thank you for everyone being part of this event and have a good day.
Hi everyone, good morning. I am Shriya Shukla. I head up the sustainability and strategy for carbon capture at Pi Green Innovations, which is a climate tech company based out of India. Thank you, Tiffany, and the team for organizing Green Things Summit 2026 and inviting me to it. So, let's start. Again, I want to invite you to reflect on something simple but important. When we talk about sustainability today, what are we really referring to? Are we talking about real impact on the environment? Or are we talking about how well we are able to describe that impact through reports and disclosures? Over the last decade, most of us in this room, whether directly or indirectly, have been part of the ESG journey. We have seen frameworks evolve, reporting standards mature, and sustainability become a boardroom conversation. That shift was necessary and it was powerful. But what I want to explore today is what comes next. Because the next phase of sustainability is not about how well we report, it is about how much we physically change. It's about moving from intent to outcome, from narrative to measurable impact, and from ESG as a framework to carbon capture as an execution mechanism. We measured emissions for a decade. I want to stay with this idea for a moment because it is at the heart of the entire discussion. Over the last 10 to 15 years, companies have become extremely sophisticated in how they measure emissions. We have built detailed inventories, categorized emissions into scope 1, 2, and 3, and even created teams dedicated to sustainability reporting. Today, large corporations can tell you exactly how much carbon they emit, sometimes down to individual processes or facilities. But despite all of this progress in measurement, something fundamental has not changed. The atmosphere does not respond to how accurately we report emissions. It responds only to how much carbon actually enters it. And that number globally has not decreased at the pace required. So, the uncomfortable truth we must face is this: we have become very good at describing the problem, but not equally effective at solving it. And that gap is what this entire session is about. To understand why this gap exists, we need to go back to how ESG evolved. In 2006, the United Nations introduced the Principles for Responsible Investment, which marked a turning point in how investors looked at risk. Environmental and social issues were no longer seen as external concerns, but as factors that could directly influence financial performance. Then, in 2015, the Paris Agreement created a global consensus around climate action and emission reduction targets. Around the same time, the idea of stakeholder capitalism began to take hold, where companies were expected to create value not just for shareholders but for society as a whole. These developments led to the rise of ESG ratings, ESG funds, and institutional investors integrating sustainability into their investment decisions. Capital began flowing toward companies that demonstrated better ESG performance, and this changed corporate behavior significantly. But it is important to recognize that ESG was built as a system to measure, evaluate, and signal risk. It was never designed as a tool to physically eliminate emissions. In India, this evolution followed a structured and policy driven path. It began in 2009 with the National Voluntary Guidelines issued by the Ministry of Corporate Affairs. These guidelines laid the foundation for responsible business conduct. In 2012, SEBI introduced business responsibility reports, making it mandatory for top listed companies to disclose their sustainability practices. Then, in 2021, this evolved into the Business Responsibility and Sustainability Report, or the BRSR, which significantly expanded the scope and depth of disclosures. Today, ESG reporting in India is one of the most compliance driven frameworks globally. It is structured, mandatory, and increasingly aligned with international standards. This is a unique strength of India's ESG ecosystem. However, if we look closely, every stage of this evolution has focused on improving how companies report sustainability. It has not necessarily transformed how emissions are generated at the source. ESG did achieve several important outcomes. It created awareness at the highest level of organizations. It introduced accountability, where leadership teams became responsible for sustainability metrics. It aligned capital with environmental performance, influencing how investors allocate funds. But the system largely rewards transparency and disclosures. It incentivizes companies to present their sustainability performance effectively. It does not always ensure that emissions themselves are reduced at the core process level. This is where the limitation becomes visible. When we examine real industrial scenarios, this gap becomes even clearer. Consider a cement plant. The company may improve water usage, reduce waste, and increase its share of renewable energy. These improvements are meaningful and contribute positively to ESG scores. But the core process of cement production involves chemical reactions that release CO2. That emission continues regardless of improvements in peripheral areas. So, while the company appears more sustainable on paper, the actual volume of carbon entering the atmosphere may not change significantly. This illustrates a fundamental issue. ESG can optimize the edges of a system, but it does not necessarily transform the core emission source. This leads to a disconnect between targets and physical reality. Companies set ambitious net zero goals for 2030, 2040, or even 2050. These targets are important, but they exist alongside ongoing emissions that continue every second in industrial operations. The atmosphere does not respond to timelines or commitments. It responds only to actual emissions. And this is where the conversation must shift. When we look at sectors such as cement, steel, and power, the scale of the challenge becomes evident. These sectors contribute more than half of global emissions. Cement alone accounts for approximately 7 to 8%, steel contributes to around 7 to 9, and power generation contributes roughly 30 to 40%. These industries are foundational to modern economies. They cannot simply be replaced or eliminated. Their emissions are deeply embedded in their production processes, which means that incremental improvements are not enough. What is required is direct intervention at the emission source. Current solutions attempt to address this in different ways, but each has limitations. Carbon offsets allow companies to compensate for emissions by investing in projects elsewhere, such as reforestation or renewable energy. While this may balance emissions on paper, the original carbon is still present in the atmosphere. Renewable energy reduces emissions related to electricity consumption, but does not address emissions that arise directly from industrial processes. As a result, the core issue remains unresolved. This is where the transition from accounting to engineering becomes critical. Instead of focusing solely on measuring emissions, the focus shifts to altering the emission process itself. Carbon capture represents this shift. It intervenes directly in emissions. Instead of allowing CO2 to enter the atmosphere, it is captured, treated, and converted. It's not theoretical. This is physical decarbonization. This shift is being accelerated by policy and economic pressures. Mechanisms such as European Union's carbon border adjustment mechanism are introducing direct financial consequences for carbon intensive production. India is in the process of developing its own carbon market frameworks. Global agreements under Article 6 are creating new avenues for carbon trading. Together, these developments are making emissions a financial liability, not just environmental concern. While CCUS existed for last decade, the issue was they were trying to capture CO2 and inject it underground, which was impractical, dangerous, and makes no financial sense. In this context, the approach taken by Pi Green becomes particularly relevant. Across the world, different companies are working on carbon capture and utilization in different ways. Organizations like Seabound focus on onboard capture. Carbfix focuses on underground mineral storage. And Carbon Cure integrates CO2 into concrete curing processes. Each of these addresses a part of the value chain, but most of them operate after the carbon has already been emitted. What makes Green fundamentally different is the point of intervention. Instead of managing carbon after emission, the system eliminates it at the source itself through integrated capture and mineralization. The moment CO2 is generated in an industrial process, it is intercepted before it disperses into the atmosphere. It reacts chemically and is converted into stable carbonates. This is not temporary capture or delayed storage. It is immediate transformation. Once converted, the carbon is locked in a solid form and cannot re enter the atmospheric cycle. This shifts the entire paradigm from carbon management to carbon elimination. The net zero machine is built around this principle and designed specifically for industrial deployment. It captures emissions directly from the flue gas streams, works across multiple fuel types, including coal, diesel, and gas, and most importantly, can be integrated into existing industrial systems. This retrofit capability is critical because industries cannot afford to shut down operations or rebuild infrastructure just to decarbonize. Any solution that requires major redesign slows adoption. A solution that integrates seamlessly into existing system accelerates it. That is where practicality meets scalability. The working mechanism of the system is straightforward in concept but powerful in impact. Flue gas enters the unit and comes in contact with an alkaline medium. CO2 reacts with this medium and undergoes a chemical transformation into stable carbonates. Cleaned gas exits the system. The important distinction here is that the carbon is not just being trapped or filtered, it is being chemically altered into a stable, non reversible form. This ensures permanence, which is one of the biggest challenges in traditional carbon capture approaches. This also eliminates multiple risks associated with conventional systems. There is no need for transporting CO2 through pipelines, no dependence on geological storage sites, and no requirement for long term monitoring to check for leakage. Everything happens at the point of emission. This significantly reduces complexity, cost, and operational risk, making the solution far more viable for large scale industrial adoption. When compared with other approaches, the difference becomes even clearer. Offsets create a balance on paper, but do not physically eliminate emissions. Renewable energy reduces emissions related to electricity, but does not address process emissions. Traditional CCS captures carbon but introduces infrastructure challenges and long term uncertainty. In contrast, this approach removes emissions at the point of generation and converts them into a permanent form. The problem is addressed where it originates. An additional advantage emerges in the form of circularity. The carbonates produced through this process can be used in construction materials such as aggregates or bricks. This creates a dual impact. First, it ensures permanent storage of CO2 within a solid structure. Second, it reduces dependence on cement, which itself is one of the most carbon intensive materials globally. In many cases, these materials offer comparable or even improve strength and durability. This means there is no trade off between sustainability and performance. Emissions are not just reduced, they are converted into value. From an industrial adoption perspective, maturity and reliability are critical. This is where the concept of technology readiness level becomes important. A system that has progressed beyond laboratory validation and demonstrated performance in real industrial environments signals readiness for deployment. Pilot implementations further reinforce this by proving that the technology can operate under actual conditions with real variability in emissions and operating parameters. Scalability ensures that the same solution can be replicated across multiple plants and sectors without fundamental redesign. These factors together determine whether a technology remains a concept or becomes an industry standard. Another essential layer in this ecosystem is MRV, which stands for measurement, reporting, and verification. Measurement ensures that the quantity of CO2 being captured is accurately quantified using real time data. Reporting structures this information in a way that can be communicated to regulators, investors, and the market participants. Verification introduces independent validation, ensuring that the data is credible and trustworthy. In carbon markets, this credibility is not optional. It directly determines whether emission reductions can be monetized. This leads to the role of carbon markets, where emission reduction becomes an economic activity. Carbon credits are generated when emissions are reduced or removed, and these credits can be traded. However, the value of these credits depends heavily on their quality. Credits that are based on assumptions or temporary reductions often face scrutiny. In contrast, credits that are measurable, verifiable, and permanent command significantly higher trust and value. Mineralization based capture aligns strongly with these criteria, making it particularly relevant in evolving carbon markets. From a business perspective, this changed the entire equation. Sustainability is no longer just about compliance or reporting, it becomes a strategic lever. Companies can reduce their emission footprint, prepare for regulatory frameworks such as CBAM and domestic carbon pricing, and create potential revenue streams through high quality carbon credits. This alignment of environmental impact with economic value is what ultimately drives large scale adoption. When we step back and look at the broader journey, the transition becomes very clear. ESG created the foundation by introducing accountability and transparency. It made companies measure, disclose, and acknowledge their impact. But the next phase requires execution. It requires technologies and systems that directly alter emission outcomes. Net zero, therefore, is no longer just a target defined by a future date. It is evolving into a system that integrates technology, policy frameworks, market mechanisms, and verification processes. Each of these components play a role, and the effectiveness of the system depends on how well they work together. Looking ahead, the defining factor for sustainability will not be the quality of reporting or the ambition of commitments. It will be the ability to reduce emissions in real terms, to remove carbon permanently, and to demonstrate that impact with credibility. As I always say, what gets reported builds reputation. What gets captured changes the planet. Thank you. You may connect with me for your queries via mail or through LinkedIn by using the QR code.
Good morning, everyone, and thank you for being here. I want to start with a simple thought. Many companies are still trying to manage carbon after it has already happened. They measure it, they report it, they summarize it, but by the time it happened, the machine has already ran, the fuel has been consumed, the window for the changes has already happened. So, my question is, how do we explore and identify the carbon reduction happening in real time rather waiting for the report? My name is
Hello again, everyone. And as we come to a close,
Good morning, everyone, and thank you for being here. I want to start with a simple thought. Many companies are still trying to manage carbon after it has already happened. They measure it, they report it, they summarize it, but by the time it happened, the machine has already ran, the fuel has been consumed, the window for the changes has already happened. So, my question is, how do we explore and identify the carbon reduction happening in real time rather waiting for the report? My name is Sundar Subramanian. I am part of Cognizant IoT and sustainability practice. As a director, I lead the consumer goods and retail vertical. So, what if it began in the moment the machine decides how to run? That's a shift from an energy intelligence to a carbon intelligence. Energy intelligence tells us what we have consumed. Carbon intelligence tells us whether we should have consumed it in the way, the moment, an equipment is functioning, the conditions are specific to the function of the equipment, and whatnot. Especially for the industries which are leading with heavy equipments and factories, this shift is enormous because in a plant, emissions are not created by abstract policies. They are created by real operations, especially those heavy equipments such as the boilers.
good afternoon and welcome back. I'm Tiffany Nielsen, and next we're diving into one of the most important and often overlooked opportunities in the EV transition, bringing charging infrastructure to the places where people actually live, work, and spend their time. As EV adoption accelerates, we're seeing more chargers on highways and in public spaces, but the real frontier is much closer to home. Commercial and multifamily properties represent the largest untapped opportunity in EV charging. Yet they've also proven to be some of the hardest environments to deploy in. To help us unpack why and what's changing, I'm joined by Diana Seawick, an EV charging operations leader and host of the Charge Talk podcast. Diana has hands-on experience deploying and managing charging infrastructure across a nationwide portfolio, giving her a uniquely practical perspective on what it really takes to make these projects work. Diana, thank you so much for joining us.
Thanks for having me, Tiffany. I'm excited.
Me too. Well, let's start with the big picture. Most people think of EV charging as something that you see at a gas station or a fast charger. Why is commercial and multifamily real estate actually where the biggest opportunity is?
Yeah, so when you think of charging, a lot of people do think of these fast chargers where it's maybe 30 minutes to stop and charge, and that's a level 3 charge. Level 2 charging is really what is most recommended for most EVs, and that's anywhere from 5 to 8 hours. So you're going to want to charge somewhere where you're going to be dwelling for a long period of time, say at your home, at your office, anywhere where you're going to be somewhere for hours on end, so that way you can be plugged in and come out to your car fully charged. So that's why multifamily, residential, corporate offices, student housing, all of these places are really ideal for charging your vehicle. And I don't think that everyone always realizes that, because we have a lot of people who still don't drive EVs, and the EV world is still kind of new and evolving, and so not everyone understands it's not the same as a regular gas vehicle.
Thanks, Diana. And what does the electrical infrastructure situation actually look like right now in most apartment buildings and commercial properties? And what does it take to get them EV ready?
Yeah, so this is where it can be very challenging. Most infrastructure that's already built wasn't thought out to have room on the electrical panels for electric vehicle charging stations. So oftentimes, if it's an old building, old apartment building, it may not have a whole lot of space on the panel, to add to. So you've got a lot of things to think about. You may need to have upgrades. It can become a really big project. Now, obviously, people who are building brand new builds, brand new office buildings, brand new apartment buildings, are aware of this and making those steps to where they're leaving more space on the electrical panels. But if you have an older building, it's a challenge, and every building's different. So that's where we come up against a lot of different issues.
I can imagine that retrofitting would be pretty difficult. And
Yeah.
what are the biggest hurdles that property owners face when they consider adding EV charging? And how are those different depending on whether it's an apartment complex, an office building, or even a hotel?
Yeah, so it could become very costly, because you're going to think about, you may have to, break ground to add more conduit. Like I said, you may have to upgrade your infrastructure and add more power. All of these things can cost a lot of money, and a lot of these properties may not have that in the budget. So it can be a daunting kind of task to look at as far as adding that feature to your property. Especially if you don't know what you're doing, it could be even more costly because you're just kind of blindly trying to figure it out. So it's important to work with the right people.
Thanks, Diana. And there are new business models emerging that make EV charging possible at no cost to the property owner. How does that work, and what should owners be looking for?
So I think these models can be really, really helpful, especially to folks who I was just mentioning in the last question. It can be very costly. So really looking for those models where you don't have to pay anything up front, or you pay very little up front, can be so helpful in getting this amenity to your property. Something that I think is really important is really handling it from the beginning to end. A lot of companies out there will just sell you the EV charging stations, and then you'll never hear from them again. And at the end of the day, you really want someone who comes in and kind of holds your hand and walks you through it. Like I said, people don't understand the EV world still. It's still kind of new. So really being transparent, letting them know from start to finish what is happening. And then at the end of it all, being there for maintenance, being there for client success, keeping the relationship going. That is huge, because if something goes wrong with the EV charging stations and they're offline, and you've got people who need to charge in order to get to work or get home or whatever, and you can't get a hold of the manufacturer who sold you the EV charging stations, that's just more problems. So really, making sure that you find someone who keeps that relationship going is a really big plus.
Those are some great points. And you've personally deployed and managed stations across a nationwide portfolio. What surprised you most about what works and what doesn't on the ground?
Yeah, so going back to the last question, I think that really having that relationship is huge, and making sure that you are, communicating with the person who installed and is taking care of your EV charging stations. But also, it's really important to educate. So, whoever is taking on the EV charging stations, having them installed on their property, make sure you educate them on how to use the stations. Make sure you give them enough information to help them be excited. It's hard when you install EV charging stations on a property and the people don't understand or want to tell everyone about them. If there's not excitement around what that new installation is, then people may not even know that they're there. People may not utilize them. And so it can go flat as far as, if people aren't aware of the EV charging stations, well, they're not going to get used. And then what did you do this for? Right. So really and truly getting people excited about it, and then just keeping that communication, that relationship going. I think those are really two big things that I've watched and seen, especially just working with so many different EV charging station brands.
Thanks, Diana. And grant funding is a big part of making these projects financially viable. What advice would you give to someone who's never pursued competitive grant funding before?
Grant funding. Yeah, that is one wild animal. I definitely think that the most important thing is, before you do anything else regarding the project that you are about to work on, look into grants and rebates. There's a lot of small details that they are very, very strict on. So you want to make sure that, you find out all of the rules and all of the eligibility. So that way you don't, make a misstep and then find out that you're not eligible for thousands of dollars, right? So I know that that is the number one thing that I always am very careful with when it comes to that sort of thing is, find out, do you need to apply before you even break ground, before you even purchase a station, like before you do anything else, do you need to apply for this grant to be approved? And then just really doing your research. You may, go on Google and search and see if there's something available and maybe find nothing, but there's other search engines out there that are a little more in depth. And so really exhaust look under every rock, every nook and cranny, because there's programs cropping up all the time, and you don't want to miss out on thousands of dollars that you could be getting in, grants and refunds for your EV infrastructure. So really be diligent there.
Great advice. And for property managers, tenants, and anyone in the sustainability space listening today, what can they do right now to help accelerate EV charging adoption in their own communities?
Good question. I would definitely recommend being vocal. If you want to see EV charging where you live, where you work, ask for it. Find out who is at the top, ask them, get people around you to co-sign. The more people you have that are demanding something, the more chance you're going to get what you want. So really, they say the greasy wheel gets the squeaky wheel gets the grease, right? So be vocal, ask for EV charging infrastructure, find out who you need to talk to make the needle move, and really be passionate about it, because the more people who are demanding it, the less that they can ignore, the less that they can put it off,
Thank you, Diana. And I do have some questions for you from Q&A. So what are the biggest hidden costs that people don't plan for?
I would say, again, going back to infrastructure, if there is need for upgrades in the panel, when it comes to not enough power on the property, I think that can be costly, because sometimes you'll have to, pay for permits, trenching, and then labor. It all starts to add up, and it can become thousands of dollars. So definitely, you may think that you're getting into a small project, and then all of a sudden, you find out, well, you don't have enough power, and you've got to dig into concrete, and that's all going to cost a lot of money.
I can imagine that's the case with many small projects. And
Yeah.
so here's another one for you. What advice would you give to smaller property owners who don't have large portfolios or resources?
That's a good question. I would definitely go on the grants and rebates route. I would say if you are a small player and you don't have a ton of budget, I would go straight for that. And then also, there are companies out there that will work with you. There, like we talked about that zero cost model. There are companies out there that will um, put up all of the infrastructure for you at no cost. There'll be financing options. There are options where maybe you don't own the stations, but you can have the stations on your property and do a revenue share. There's a lot of different models out there, so I would say do your research. You never know what's available. If you want something bad enough, you can make it happen.
Great. And how early should property owners engage with their utility, and what should they be asking?
I would say the minute you decide that you want to add EV charging to your property, reaching out to your utility is probably one of the first steps that you want to take. I know in my experience, it usually comes down to we'll have a electrician walk the site, find out what's available on the electrical panel, because EV charging stations need to be within 150 feet of the electrical panel of where the power is going to be coming from. So really and truly, it starts with the electrician finding out what's possible, and then from there, then you would most likely engage the utility if you're going to need upgrades.
Great. And what happens when demand outgrows the initial installation, and how do you future proof?
Oh, that's a good question. So, what I've noticed working with properties is really and truly you want to be conservative in the beginning, right? Especially if you don't have a ton of EV drivers to start with. Just start with one or two EV charging ports, and if you want to plan out for the future, you can. But really and truly, the way I've seen it is cross that bridge when you need to come to it, because like we stated earlier, things can get pricey. And there are grants and rebates available, and there are utilities that will work with you. There are a lot of programs out there that the utilities will try and offer certain things to really help out with adding power. But at the end of the day, always start conservatively. And I know things are getting a little rough right now in certain states where they're really adding all of these. You've got to have 20 to 40 ports on your property to even open the property. So at the end of the day, it comes down to, if you are building a property, just make sure you're set up. It's much cheaper when you're building versus, like you said, retrofitting, Tiffany. Retrofitting, it's just keep crossing that bridge when you come to it. And if you have to upgrade your infrastructure, then that's something that you'll have to budget for, possibly.
You're doing great, Diana. I've got some more questions. What should property look for when choosing a charging provider or partner?
So I think really and truly it comes down to relationships. I will beat that horse until the end of time. You want someone who is listening to you. You want someone who is transparent with you. You want to know what you're getting. You want to make sure that someone is going to be there after the EV charging stations are installed. So that way, if anything goes wrong, you can get a hold of someone and find out, like, how can we troubleshoot this? What's going on? and really just make sure that someone is always communicating with you so that way you're never left in the dark. So if you can find a provider that gives you white glove service, gives you concierge service to where you know what's going on and you're being taken care of, that is the number one thing I would look for. If they're just going to sell you equipment and you may never hear from them again, do not start up with them. It's not a good sign. So
Great tip. And Diana, how do you manage demand when there are more EV drivers than available chargers?
right. So we always start very conservatively whenever we install. And here's the thing too: people will be concerned about not enough EV charging stations, but really and truly, you don't need to charge every day unless you're an Uber driver. That's probably the only person who would need to charge every single day. And so you really want to look at like how many EV drivers are on the property, because they're not going to be constantly filling up every day, just like we don't fill up gas every day, right? So really and truly, you want to make sure that you are just looking at how many EVs are on the property. Now, if it becomes this thing where EVs are not able to plug in and you need to add more stations, that's something that you can definitely do. You may need, like I said, you may need to upgrade your panels if you don't have enough power. But oftentimes, if there is enough space on the panel in the beginning, you can just install one or two ports and then look on the panel and see that you have space for more, and just leave open spots for more charging stations to add later on down the line. So, because at the end of the day too, you got to realize these charging stations have network fees that you've got to pay for regardless of if anyone's using the stations. So it can become costly if you've got too many stations on site, and it feels a little bit like awful if you're getting charged for something that no one is even benefiting from. You know what I mean?
That makes a lot of sense. And how do you avoid installing something today that becomes obsolete in a few years?
Yeah, that's a really good question. I think that the EV space is ever evolving. The technology is constantly changing. I know personally, I've worked with many, many different brands. And really and truly, though, I know for a fact that the EV charging stations that are out there right now will be working and will be usable for the foreseeable future. I think what's important is if you start working with someone, a provider, I think something that's really powerful is if they are open to down the line, installing newer technology. I think that's a huge plus, because at the end of the day, I mean, really and truly, you can compare EV charging stations to like a cell phone, like the Apple phone. People will buy a new iPhone, every few years at this point. Some people buy them every year, which I don't recommend. But so it's going to become a thing, or maybe not, who knows, because it's ever evolving. But it may be a thing where you may need to upgrade your stations within the next 10 years. It's anybody's guess, because the EV world is constantly evolving, and there's so much just even on the brink right now. We've got robo taxis that are just becoming more and more, they're being deployed more and more, and that's going to add a big change to charging as well, because you don't have a person to get out and charge that vehicle, right? So that's going to add a whole other dynamic to charging those robo taxis. So there's a lot of factors. So it's anyone's guess, honestly. But yes, I do see that as a factor of machines becoming obsolete. It's definitely something to be aware of.
Well, to your previous point, I would say it could almost be like leasing. Like you're leasing a car, you just lease the EV.
Mm-hmm.
That way, the people that created it back, and then they could upgrade it, and then they could release it again. That makes a lot of sense.
I think that's a great idea. Yeah.
Well, there's another one for your playbook there, Diana. And I've got one
Yeah.
question for you. What trends or technologies should property owners be paying attention to right now?
Trends. I think that
Trends or technologies?
trends or technologies. I want to say, obviously, the robotaxi trend is massive. The one I was just talking about. That is going to be revolutionary. I know fleet charging is absolutely huge right now. You've got just all of these companies that are taking their semi trucks and their delivery trucks and they're just turning over to EV. I mean, you see them on the road all the time, you know? So I would say those are two really big trends, the autonomous driving and the delivery. Those are huge, and they already are, but they are going to continue to have an impact on the charging infrastructure and just how it's done.
Well, thank you so much, Diana. That was very informative. And if there's one thing that stands out, it's that the EV transition isn't just about vehicles, it's about infrastructure, partnerships, and rethinking how properties serve the people who use it every day. So, commercial and multifamily real estate may be complex, but as we've heard today, the barriers are starting to come down thanks to new business models, better funding pathways, and real world experience from leaders like Diana. So, Diana, thanks so much for sharing your perspective and for the work that you're doing to move the industry forward. And also, thank you to everyone watching for joining us. And we hope this conversation leaves you with a clearer sense of the opportunity and the role that each of us can play in accelerating EV adoption.
Thanks, Tiffany.
All right. Thank you. Bye-bye. Hello again, everyone. And as we come to a close of the Green Things Summit 2026, I want to take a moment to reflect on what we've explored together today. And more importantly, what it signals for where we're headed. We began with our opening panel, where we grounded the conversation in a simple but powerful truth. Sustainability is no longer a side initiative. It's becoming core operational infrastructure. Across AI, IoT, edge computing, and energy innovation, the message was clear. These technologies only create real impact when they're connected, aligned, and executed with intent.
And that focus on practical use was visible in every session. In Suhir's Belal's keynote, we were asked to think differently about the hidden cost of AI. As AI grows, so does the energy it uses. Power observability is not just a technical feature anymore, it's becoming a basic requirement for building cloud systems that are actually efficient. If you cannot see where the energy is going, you cannot manage it well.
Then Dr. Scott Gerard expanded our thinking even further with the idea of a composite mind, where intelligence isn't centralized but distributed across cloud and edge systems working together. That model of multi-agent, multi-environment intelligence isn't theoretical anymore. It's becoming essential in real-world systems where reliability and autonomy matter.
We also looked at how sustainability connects to resilience and energy security. In Maureen's Kinua's fireside chat, we saw how renewable natural gas can turn waste into something useful. It can strengthen local energy systems and help reduce emissions. That was a good reminder that progress does not always come from something brand new. Sometimes it comes from using existing resources in a smarter way.
And Shreya Shukla pushed us to confront a hard truth. ESG got us started, but it's no longer enough. The shift is now toward measurable, engineered decarbonization through carbon capture, better measurement systems, and stronger alignment between policy, markets, and technology. It's about closing the gap between what we say and what we can actually reduce.
Sundar Subramania took that a step further by asking us to think about carbon differently, not just as something we measure after the fact, but as something tied to decisions in the moment. If emissions can shape and are shaped by everyday operational choices, then our systems need to help guide those choices in real time. That's where the conversation starts to move from energy intelligence to carbon intelligence.
And finally, Diana Seawick brought us down to ground level, literally, by looking at EV infrastructure in the places that people actually live and work. And what stood out wasn't just the opportunity, but the complexity. And yet, with the right models, partnerships, and persistence, that gap is starting to close.
And if there's one thing that connected today's sessions, it's this. The issue is not whether the technology exists. It clearly does. The real question is whether we can apply it well. We already have many of the tools and ideas we need. What matters now is putting them to work in a coordinated, practical way.
And that's exactly why events like this exist. And we want to thank all of our incredible speakers for not just sharing ideas, but for sharing real world experience on what's working, what's not, and what needs to change. And a special thank you to our sponsor, Knowledge Reactor, for supporting conversations like this and helping bring the community together.
We also want to thank all of you, operators, builders, leaders, and thinkers who are doing the hard work of turning these ideas into something real.
And of course, thank you to IoT Marketing and TechScope Connect for hosting and convening this summit. This is exactly the kind of cross-disciplinary dialogue that moves the industry forward.
And before we wrap this up, we want to invite you to continue the conversation with us. On July the 23rd, we'll be hosting our next event, the Intelligent Thinking AI Summit. If today focused on how technology can support sustainability, the next event will look more closely at how AI systems are changing, how they reason, make decisions, and operate in complex environments.
And it's a natural continuation of everything that we discussed today, from multi-agent systems to real-time decision-making to the infrastructure required to support it all. And the Intelligent Thinking AI Summit will also feature thought-provoking sessions such as the ACT or ACT Framework for Responsible Innovation by Yumna Asen and the Governance Illusion on Shadow AI by Campbell Robertson. So be sure to register and attend, and you can do so on either of our sites, iotmktg.com or techscopeconnect.com. And we also have speaking and sponsorship opportunities available, so please reach out to us for more information on these opportunities.
And before we go, we also want to invite you to watch the TechScope News podcast, where Tiffany and I talk through some of the most important developments in AI and emerging technology. If you enjoyed today's conversation, that's a great place to keep it going. Until then, take what you heard today, ask better questions, make smarter decisions, and put it to use.
Thank you again for being part of the Green Things Summit 2026, and we'll see you all next time. Bye-bye.
Bye-bye.